Okay, I think we can bring them on.
Yeah, I've started, sir. Now I got the YouTube link. I clicked on it. It says connected to YouTube.
Okay.
So I'm adding Sudhir sir also.
Yeah.
Saha sir, he has joined.
Okay. Professor Seul Jung.
Yeah, he has been added.
I don't see him.
He has to switch on. Professor Jung, can you please turn on your camera and mic? Yes. No. Yeah, he
Yeah.
is
Okay.
turning it on.
Okay. Anybody else for this session? Is Ashokan there?
I'll just check. No, he hasn't joined yet. That's it. Actually, Dr. Jagannath Raju had joined one of the tables he was testing. So
Okay.
I'll just probably message him later on
Okay.
that we have come here. He has joined here. Yeah, he has joined from two devices. One will be iPad for video and one will be desktop for sharing the screen.
Okay. Let's see how that goes. Okay. I think we can start, right? Yeah. Okay. Good morning to everybody and welcome to this third day of the International Conference, Advances in Robotics, AIR 2021. Today is the third day, and the first plenary speaker of the day is Professor Seul Jung, who is a professor at Chungnam National University, Daejeon, South Korea. Professor Jung obtained his PhD from the University of California at Davis and is currently a professor in the Department of Mechatronics Engineering. He'll be talking to us on balance mechanisms and control in research and life. Okay. His work is very interesting because he also does mechanisms design and how to balance real world applications. Okay, Professor Jung, please welcome and thank you for agreeing to be a speaker in AIR 2021. And please make your presentation.
Okay. Thank you very much for a kind introduction. I thank you, Professor Chair Ashisha Tuta, okay, and then also co-chair Tomohiro Shibata from Japan. Also, personally, I like to thank Professor Subir Kumar Saha for inviting me to give a plenary talk. So my talk is on the balancing control in research and life. So, kind of the title is weird. Balance control in research and life. I like to share some personal things that, before COVID-19 crisis, came. So this work has been done my research years in Korea, okay, and then I like to share Korean research subject with the Indian colleagues, okay. Okay, so this is a overview.
Can you please share your screen? We are not seeing your screen.
Oh, how do I do that?
You can just share. There is a share button.
Oh, I have to share here too?
Yes. Yes.
Okay. Sorry about that. Okay, sorry about that. This is new. Okay. So, my topic is balancing control in research and life. So why life? Because we are fading with COVID-19 here. So that everybody's life has been changed due to virus. Okay. So this is just the overview of my homepage, my laboratory homepage. Basically, what we are doing is that we are actually developing intelligent mechatronic systems, such as intelligent robot and other mechatronic systems, to help human being in various aspects with some control algorithm, intelligent algorithm, from design to hardware, software, everything. So that is the what we are doing. Okay. So my talk is organized like this: balancing nature and our lives. And then, why do I conduct research in this area, research motivation, and I like to introduce some of the control theory we are using to implement the system integration. Some disturbance observer, a time-delayed control, data-driven control approach, and intelligent control approach, and some force control to interact with environment, from robots. And then I like to share some typical robots, creative and particular robot, and I'll conclude my talk. So starting with the video, okay, this is one of the most gorgeous place in Korea called Jeju Island. So nature is quite preserved, well preserved, and then the World Natural Heritage recognized by UNESCO. 10 years ago, majority of Korean newly married people go there for their honeymoon, but now they went to all over the world. But this place is nature is well preserved. It's very good to visit there. So I like to share some of the video about Jeju Island. Okay. Also, that this October, the conference, one of the largest international conference in Korea, ICAS 2021, will be held in Jeju Island. So Jeju Island is also visa-free island, so that you can easily come and visit there. Okay, so my life, I like to share my life. Okay, my advisor is Steve Shah. He is here, and then my family is here. So whenever I visit the United States, I visit him because he is getting old. So that one of my former advisor is Richard Dorff, Dick Dorff. He is famous for his book, Modern Control System. He was the my PhD committee, but he passed away 2 years ago. So I'd like to dedicate this talk to my former advisor, Steve Shah and Richard Dorff. My education and research life is like this. I like the student, especially younger student, in order to motivate them, okay, robotics area, mechatronics things, so that I invite them to laboratory to show some of the robotic, out products, so that high school student can visit. And then also I participate in engineering camp for high school students, so that they visit us to look around laboratory. Although in your laboratory is not that big, it's small, but small space can produce bigger things. Okay, it's depending upon person. Okay, not facility. Okay, if you have a good facility, then it's okay. But although small facility, if you have good people, then you can have a better output. Okay, and this is a 19 digital circuit project. For sophomore. Okay, at the end of semester, they present project of their build, so that we evaluate it. So this is due to the COVID, everything is gone, so that we do everything online, not offline. So that is our limitation on our lives currently. So another national competition is a creative intelligent robot contest. There are two categories. One is a line tracer performance, and then another is a creative robot, performance. But this one also last year online competition, okay, and this year August also online. So personally, I like to visit the Africa, to meet younger student to give some motivation to them. Okay, and then from India, I had very good 4 students internship. Actually, there are 4, but 3 of them came again to present paper. Okay, one of them is co-author together. Manoj and Aniket was a co-author, so that Jurejan actually came to present paper. DT, Dhruv and then Kuma, and then they work very hard and then present poster paper 2019, I guess. Also, I have visitor professor from IIT, and then Adnan from professor student visit our laboratory. Also, I visited NIT Calicut last year, February actually, so that we attend the Robotics, Artificial Intelligence, and Control Symposium, so that I have learned many things from Indian colleagues. Also, my student and other students actually had a good time with the Indian student as well. So that they have a good time over there with the Indian students. Actually, some oceans, beaches. Okay, so this kind of peaceful and friendship actually now is banned due to the COVID-19. Okay, so I like to when the balance is broken, then that everything is will be disaster. Okay, so I like to share some of the human disaster in Korea. Back in 1995 June, one of the largest department store in Korea actually suddenly collapsed. Okay, so that many people died by that casualty. Okay, so it is not nature, by it's by human fault. Okay, maintenance fault. So we have big disaster there. Similarly, June 24th, about 2 weeks ago, I guess, 1 week ago, or in Florida, same thing happened. Okay, the apartment suddenly early in the morning collapsed, so that many people are still missing there. So they are still, searching for the missing. So it is now we are facing with COVID-19 as disturbance to our life. Okay, so that suddenly from China, COVID-19 spread all over the world. Actually bothers human life. Okay, so we are still suffering from the casualty of COVID-19. So our life, okay, should make distance with the people, so they cannot make friends anymore, and the activities with people have been banned. So this is current our life. So then how can we fight back to disturbance? We have to control the pandemic, and we have to regulate the people activities, and then we have to get the vaccination in order to reject disturbance. Okay, so same thing can be applied to a system in my research. So as I explained, keeping balance in nature and our lives is quite important to enjoy stable and peaceful life. Okay? So research in balancing mechanism and control to make systems stable is very much required. So when I was a graduate student, Rafi Zadeh from UC Berkeley came to give us a seminar. Okay, came to our campus to give a seminar about inverted pendulum like this. So he demonstrated to control the pendulum, the balance, but very difficult. Okay, so he introduced a fuzzy algorithm, one of the intelligent algorithm to control inverted pendulum at the time. So I was, impressed. Okay, human cannot do it, but algorithm of a robot or system can do it. So how can we do that? Okay, how can the system can do that? So I had interest in that balancing concepts. So my research has been inspired by balancing concept at the time. So our body, by itself is a balancing system. So it can be modeled as an inverted pendulum. So in the control textbook, we have inverted pendulum system as a nonlinear example. Okay, that is the my motivation of balancing mechanism and control in system research point of view. Okay, so then how to maintain balance in system? Okay, not the lives. Okay, so I maybe categorize in two. One is passive, and then the other one is active. So maybe passive balance is based on the mechanism design, and then such as you design the system initially to make have a symmetrical design. Okay, so maybe you can apply some kinematic compensation to that, and then some parallelism algorithm to have a self-balancing, and then some fractal design to reduce the vibration in your system. So I categorize it as a passive balance. So what if you have active balance? Active balance require some control algorithm and regulation so that you actively involved in controlling the system in the active way. Okay, there are some algorithm there, intelligent algorithm, and you want to reject the disturbance, and then you want to have robustness in the system. Those are active balance schemes. But to have successful performance, we need to have both passive and active balance mechanism. You have to do this and you have to do this, and both have to be satisfied. Okay, so some of the example I share, passive balance. So a long time ago, we tried to develop something conceptual, personal transportation vehicle. So like a Segway, but not standing, but sitting, two-wheel Segway style robot like this. This one is very stable with 4-point contact. So this is more balanced, but this one we have to do apply active balancing algorithm there. And then some of the conceptual, you may use the unbalanced phenomena to entertainment, so that maybe we have some vehicle that can enjoy unbalanced mechanism, something like that. In the campus and then or research park, a long area, we may have some kind of riding share mechanism there, so that we have many vehicles to run regularly, following the invisible line, which is line tracer concept. Okay, and then some other concept was cooperation between two vehicles, a drone and a land vehicle like this, so that drone can take off from here and then come back to recharge and something like this, so that this kind of cooperation actually give a synergetic action to the performance of the task. Okay, because the robot on the ground cannot see far from the current position, but drone actually can see and monitor what happens over there, so that drone can inform this robot, okay, hold, or something like that, move slow, and or avoid detour to other paths or something like that. That is kind of a collaboration between two vehicles. And then this one was a conceptual design of our primary service robots. Okay, so at the time we think that our home service robot look like this, has a multiple functionality of manipulation and mobility to move around our home. So some typical functional capability of this robot is that the chest upper part can up and down, move up and down to reach higher object. Okay, so that is there, and then also it has a homing mode to go back to recharge by itself. So, okay, so they go to the home and stay there, okay, and recharge. All right, and then also that robot can be separated into two parts. It's a manipulation part and then mobile part. So that manipulation can be charged separately and mobile part can be charged separately. And this mobile part can work for cleaning the room. So that, vacuum is there, so that, it's an autonomous cleaning task can be done by bottom part. So then now robot is cleaning the room by itself. Okay, that is the concept of this kind of home service robot at the time. Okay, then another functionality of this robot is mode change. It's a 4-point contact to balancing mode, two-wheel contact. Okay, so this kind of mode changing is there. And also the lifting problem, so that the upper body can slide in the plane, so that when the arm hold the heavy object, it's in order to maintain the balance, we have to have some mechanism to maintain COG at the center. So that was the conceptual design of our home service robot. Okay, another passive balance design. This is actually work by Dr. Juba. Okay, so he has a specialty in the flexure design. So the flexure design is introduced to minimize the vibration in the XY plane, while we apply the motion of axis in G axis here. So, in our laboratory, we developed the foldable robotic arm, which is a kind of a soft robotic arm attached to a drone here. So, if you look at the video here, left is the without fracture mechanism, and right is with fracture mechanism. So, if you look at the cleaning the bird dropping on the solar panel, this one has more shaking. I mean, the vibration, more vibration is there. But this one is actually vibration has been suppressed a little bit. So I think fracture mechanism actually help to reduce the vibration. Okay, so actually we experimentally confirm. Although the work by Dr. Juba, he is working on a parallelogram to have the gravity compensation. So how can we design the robotic arm with gravity compensation, so that this is the initial prototype design of the parallelogram. Okay, so this is without, and this is with parallelogram design, so that this one just drop it, but this one just hold there. It's a gravity is compensated. So now is just the initial design, but later on maybe we can develop more arm-like robot. Okay. So far we consider those as a passive balance. Now we are applying control algorithm, some intelligent algorithm to have active balance. Okay. So what if we have only passive balance, but not with active balance? Then we have disaster or falling down. But if you have a active balance of controlling, then you can easily maintain control. So I'm talking about active balance here. So I categorized active balance in 3 parts. Active balance can be achieved by regulation. Regulation actually requires control algorithm. Active balance can be achieved by disturbance rejection. So external, internal, we have to deal with both internal and external disturbances. So that disturbance can be rejected by disturb observer and some other robust control algorithm. And then active balance can be achieved by system change and environment change adaptively, so that learning is involved here. So adaptation can be done by intelligent control. So based on these three categories, we are using control algorithm appropriately. So basic fundamental control algorithm, PID control, as you know, proportional, integral, derivative control. This is used most in the industry. About more than 80 or 90% of industry using simple PID control algorithm. So we are using PID control for mobile robot control. So we define the error and then PID. Okay, so we control mobile robot. And then also we can use a PID control for robot arm movement. But in industry, not only the PID control, but also some compensation, gravity compensation, actually improve the position control. So that this scheme is mostly used in industry to control the robot arm. Okay. So that here it's a simple mobile robot to collision avoidance and act back into original tracking. So we are using PID control in this case. Okay, so it follows the line. The electric car. Okay, the autonomous driving. Actually, it's a line tracer. You can consider those autonomous driving car is a line tracer, but line is invisible. But here, line is visible. That's the only difference. So that you can make an invisible line, then car is following that invisible line by sensors. Okay, so I think then same. It's a same category. And then this one is we have 3 wheels on the base. It's a omnidirectional mobile robot, and then we have a 3 degree of freedom robot manipulator. The reason we developed this robot is that the actuator, the mobile base is controlled by DC motor, and this arm is controlled by AC motor. So that I try to give the student to have experience on both DC and AC drive, so that it's a combination of the system, DC drive and AC drive. So we developed this. Okay, so it takes time. So I skip using the movement in omnidirectional. Okay, so like this. It's omnidirectional. Since this is omnidirectional movement, the movement is quite slow. Okay, and then also arm is moving, so that we can use this as a indoor service robot. Okay, so this is a 3-wheel base. Okay, then we reduce the wheel to 2 wheels. So for PTV, personal transportation vehicle, such as like 2-wheel base. Okay, initially we have a caster here to maintain 3 contact point, so that we make the vehicle stable. Okay, then we can change into mode change to 2-wheel balancing. So indoor and outdoor. So it's kind of short travel distance vehicle, so that you can go around in your campus to visit there. Okay, something like that. So he is very cautious. At the time we developed this, but the safety was not guaranteed, so that he was very cautious. So here, if you look at the mode change here, upper part video, mode changing to 2-wheel balancing mode. Okay. Okay, so the algorithm we are using here is only a PID control. Okay. Okay, so PID control can work to balance a two-wheel system. But later on, we add some other intelligent algorithm to improve balancing performance. Okay, so this is a single person personal transportation vehicle. So later on, it's too lonely for single person, so that we make two-person sitting balancing mechanism vehicle here, so that it's a little bit large. The good thing about two-wheel mechanism is that you can actually turn 360 degree in narrow space. Okay, this is a good point about two-wheel balancing robots. Okay, so that we actually test balancing mechanism of single person and two person. Okay, so now controlling the balancing mechanism, my student actually remotely control the rotation of making balancing. Later on, we make a single wheel robot to move around. Okay, something like this. Okay, and then now it's reduced. The number of wheels is reduced to single wheel. Okay, so here using the control moment gyroscope, we actually control the yaw angles. Okay, so that maintain balance and turning and driving. And this is very unique and interesting single wheel robot. Now, in laterally, we control the angle by ducted fan. So not CMG, not motors, but wind. So you blow the wind in lateral direction to maintain balance. Okay, so this is quite interesting and unique design at the time. So this is actually capstone design by senior student at the time. And we developed sphere type robot. Inside is a CMG there to make orientation. So you turn the robot, okay, so make orientation, and then driving mechanism is motor is there to make drive. Okay, so it's a kind of a sphere robot. Okay, so actually we tested in outdoor as well. Okay. Okay, now we need some other advanced control algorithm in order to upgrade the performance a little bit from PID. So we use time-delayed control here. So time-delayed control is kind of a disturbance observer. So time delay, the name of time delayed is after that using previous sampled information, so one sample delay information to cancel all the dynamic except inertial force. Okay, so we need three things: inertia matrix, fast sampling time, because time delay is bad influence on stability, right? So, and then we need acceleration signal. So three components are required to form the time-delayed control structure. So simply, this is a dynamic of robot equation. So here is a inertia, and then all other dynamics considered HT. Okay, HT can be estimated by previous sampled information, and using this HT, so we can form control law. It's very simple. This is PD type, okay, PD type, and then delay and acceleration estimation. So control block diagram look like this. Okay, we need inertia, sorry, okay, and previous torque and acceleration signal. So control block diagram, PD control, and time-delayed control. Very simple structure. Then we use those techniques. So DOB and TDC are interchangeably used. For the attitude control, we developed the quadrature system in our laboratory. So we are controlling the attitude. Previously by PD control, now we are using TDC and disturbance observer. So it's a kind of, disturbance can be canceled fast so that we have better attitude control. So using that control algorithm, we develop hybrid quadrature system, which means the hybrid means here is a flying and driving, so that my student actually controlling driving test following the trajectory. And then how can we do that? We have a tilted rotor there. And then later on, we try to have a more fast maneuverability so that we make smaller size so that drone can fly fast. So we test many times in our school to have the good performance. Okay, so during the winter and summer, it doesn't matter. We work hard to develop better drones. So that is one. Okay, these are just testing the attitude control. Now we extend those concepts to haptic. So what it does is that it's a teleoperation control. We have a force sensor here, so then haptic device can feel the contact force. So that initially we intend this robot to change the bulb on the ceiling, high ceiling, but just showing this concept, we stop there. And then this one is also interaction between the drone and human. We have force sensor here to interact with the human, okay? And the marker here is to identify orientation and position. If you have a camera up there, then you can actually control the orientation. Okay. Also, the time delayed control can be used for fast movement of two-wheel algorithm, so that it can move and then make stable, so that we can compare PD control and TDC control at the time. Okay. Also, we actually apply the time delayed control in real robot arm. Okay, so what it does is that it follows a circular trajectory, and then we have desired and actual is a quite overlap. So which means error is quite small. Okay, but if you have a PD control or PID control, you have some tracking errors there. Okay, so our result is to minimize those errors by TDC control. So we have quite good tracking performance. Okay, and then another control algorithm is the data-driven control. Okay, using the input-output data to model the system. Especially in robot, we want to have independent joint control. Each joint can be modeled as linear second-order system. Okay, so we assume we ignore the uncertainty there, and then we want to model as a second-order system. So we use recursive least square algorithm to model it, second order, and then use that model to estimate acceleration signal by using state observer. Why? Because the TDC, time delayed control or disturbance observer require those models. So we want to have accurate model estimation. Okay, so we use that data-driven approach to real system here. So the robot actually now collecting the data, input and output data, so that for certain time to model the system. Then after that, they perform some controlling the robot arm like this, so that we can have accurate positioning control achievement. So this is called data-driven control approach. Okay. Okay. So this can be also applied to synchronized control over two CMGs. Okay. Assume that two CMG are located separately, remotely. Now we are controlling the movement of one CMG. So here is that, my student is controlling the gimbal angle. Inside here, flywheel is rotating, okay, in order to induce the gyroscopic torque, okay? But, when you do developing a CMG like this, CMG has a problem with drift, okay, because it is not exactly symmetrical system, but it is a rotating system. So that as time goes, it is drift. The gimbal angle is drift. So that we actually prevent drifting by control algorithm there, okay, actively. Okay. So this can be either can be master and a slave. Okay, so we can use this kind of things as a sensor as well, contact force sensors. Another control algorithm is the intelligent algorithm. I'm using neural network control algorithm. So assume that you have the primary control system, like you already have a PID controller here, or sliding mode controller here, and any other control algorithm to control the system here. But inside or outside, there should be an uncertainty there. So I want to take care of those uncertainty from outside. So we add neural network to do that. So this is called reference compensation technique. So important thing here is that to develop training signal online. So this is purely online. So I'm running out of time, so maybe quickly. So we test on the 2 degree of freedom inverted pendulum on mobile robot base. Okay, so now the pendulum is moving circular trajectory without falling. Okay, so if you have a disturbance from outside, okay, mobile robot is moving, then also it actually successfully maintain balance, okay, with intelligent algorithm there. Okay, another thing, intelligent control algorithm applied to two-wheel mobile robot climbing up slanted surface. Why do we need intelligent control here? See, on the floor, okay, you set the PID control gain, but does not work on slanted surface because environment has been changed. Then PID gain also has to be changed. But intelligent algorithm automatically adapt to environment so that it can successfully balance its movement. Okay, so okay, rotation. Okay. One good thing about this one is the wireless compensation, not the wired. Okay, previously we have wired, but wireless compensation. You have an independent, system here, like drone. Okay, it has an inside controller, but you have a ground station. Actually, it has GPS, so that you can actually control the position control of your aerial vehicle. Okay, so that has been applied to our teleoperation task of mobile robots. So what it does is that we have mobile robot with force sensor here. So this robot actually detects the contact force. Okay, so this is a haptic device, so that we feel the contact force through the internet. And then the reason of using neural network here is to mimic Smith's predictor. So internet has the time delay. So we want to compensate those time delay by neural network, because time delay is not fixed; it's time varying. Consider as nonlinear things, so that neural network actually compensate those time delays in internet. Okay, and some other things, learning-based control, so gesture recognized and learned by computer, and command robot to move forward, backward, turn left, turn right, and something like that. So we can apply the learning technique. Okay. For force control algorithm, in order for the robot to interact with human or other robot and other environment, we need a force control. Not only the position control, but force control is required. Only position control cannot perform any task about interaction. So we need force control. So there are major force control algorithm: impedance, hybrid impedance. So, depending upon your task, you have to select which algorithm performs better. This is simple hybrid impedance control algorithm. So we have a force control loop here, position control loop here. We have switching. Switching means directionally. We set force control, position control separately. So we apply impedance force control onto balancing system. We have two-wheel balancing system like this. We have force sensor here. My student is applying external force, 8.5 Newton, to the robot system. So to maintain balance, somehow this robot has to interact with my student, so that we can maintain balance. So it's kind of a switching control from position to contact to position control. So now my student suddenly dropped the box from the contact to free space, so that we want to see that stability is maintained or not. Something like this. All right. And now we practically we can apply force control algorithm to massage robot. So we are testing some control algorithm. Force control algorithm here, hybrid impedance control here applied, follow the sinusoidal desired force. Initially we have force overshoot and some chattering follows the desired force. And then we apply the explicit force control algorithm. Explicit force control is the PID, of force error. So we apply to my student actually, he devoted himself to be a test bed. Although it is very dangerous. So now we are regulating 10 Newton force on the his arm. So that we have about 2 Newton overshoot, and regulating is good. What if my student is moving? So that environment is moving, different position, different stiffness maybe. So if we do that, you have overshoot, a little bit overshoot, but it's less than 2 Newton. So which means this algorithm regulates desired force very well. 2 Newton does not harm human arm, so that I think that it's acceptable. So this test conclusion of massage robot. Just a moment. You have a impedance algorithm and hybrid algorithm. For soft robotics, soft stiffness, our experimental study tell us that hybrid control is better than impedance control. So if we have a larger stiffness system, then impedance is better. This is autonomous driving in our campus. what it does is that it actually finds the line to differentiate between two areas, reddish and yellowish, to follow the line in campus. Okay, this is that sphere robot inside here. So we developed the control moment gyro. Actually, they're synchronized by mechanically by using gear mechanism. Okay, previously we synchronized by active control algorithm. Here, passive mechanism here. So the inside we have a CMG. Okay. And another thing is that the Hyundai Motor Company to minimize autonomous back driving error. So error was larger than 1 meter. So that we developed some sensor mechanism and algorithm to reduce autonomous back driving within 0.5 meter, the half of that. Okay, so that's another application. And then also there's a sensor, based algorithm of mobile robot SLAM, okay, to collect the data by LiDAR sensor and this laser sensor to detect the position of the robot. Okay, the goal is to arrive at my office. Okay, so skip. This one is quite interesting. We have intelligent traffic cone such that we design the trajectory at the cell phone so that if you draw the line at the cell phone, then automatically we command the cone to move that position by using GPS signal. So that if you look at here, three cones are making alignment here, but there's error there. That error due to the GPS error. Okay. And for interesting, we developed some TWT, two-wheel transformer, which is a bicycle mode to Segway mode. We have one robot, but can be transformed in two mode. Now we have a Segway mode to balance itself. So in order to make a movement in bicycle mode, we have to control the lateral balance. So we are using the ducted fan here to make balance without falling. So that ducted fan also can be controlled. Otherwise, we cannot generate directional force enough. Okay. Another interesting is that try to give omnidirectionality to caterpillar style robot, so that we have caterpillar style robot like tank, fork crane, or heavy duty vehicle. They have caterpillar tracks there, so that maybe we can think about how can we make omnidirectional movement in lateral direction, so that we design the track like this. Rather interesting is jumping robot using the cam and spring mechanism. So we can actually develop some jumping mechanism. Okay, and then this is a gyro-driven balancing robot. Okay, so we balance the robot. And maybe we do not have much time here, so I like to show briefly about the research. Solar panel cleaning robot. Okay, so the robot is required to move slanted surface without falling. So we have a suction mechanism here to stick on the panel, and while we have to move, so that the combination control between suction and movement is very important here. Okay, so practically we have drone and then robot there to handle that robot to move to solar panel, so that our design specification is the weight is less than 5 kilograms. Okay, that is it. So For cleaning, we have to cluster the bird dropping areas. What is the effective cleaning? So we have to cluster those cleaning on solar panel. So you using compare two algorithm, K-mean and self-organizing map. So that which one is better for which case we are working on here. And then foldable arm, okay? So we, Dr. Raj, Bibraji Sutta, actually working on foldable arm. So we have an extra arm so that when you install the panel on the wall, we need more arm to hold so that we actually design the supplement robot to hold. So the control of this robot is sensors by sensor at the helmet so that move and stop and so on. And that foldable arm is used for picking up things on the ground, and then also drone. We apply those arm to drone arm to perform the task, pick up something and some other tasks. We can do it. Okay, if you change the end effector, then we can actually change the performance. Okay, so the why foldable arm? Because drone has to fly. Okay, so conclusion. So the concept of balancing control can be applied to majority of systems. So passive balancing can be done by mechanical design. So mechanical design is very important at initial step. So design should be symmetrical. Okay, a priori before active balancing is applied. Oops. So in a control system, textbook, inverted pendulum is very fundamental things. So that to me, that system has inspired me to develop, successive robots to maintain balance. So balancing control, can be done, control theory, sliding mode, disturbance observer, time delay, and intention main thing. So without theory, we cannot do it. Okay, so that basically theory is very important. So for successful balancing, combine between passive and active. Not only passive and active, but among the control algorithms, we have to combine. Okay, advantage of those algorithms. So next challenge, I like to move on the balancing control to human being. So when you get old, you are shaking. Your nervous system is old too. Then some trauma, essential trauma happens. Then your life is prohibited. So maybe, I don't know, we look at solution for that kind of balancing system. So this is the robot we developed in our laboratory. My student is write down the name of our laboratory. Here we do not apply force control. We only do position control. My student is actually do force control. All right. Okay. So since I'm behind time, okay. So this is a call for paper 2. ICAS 2021 in Jeju Island. Okay, so website is this one. Now deadline is next Monday, but you can still submit 1 or 2 working in progress paper. Okay, thank you very much. I remember we started a little bit late, right?
Yes, it's okay, no problem. Yes.
Okay.
Thank you, Professor Jung, for this very interesting presentation.
Thank you.
So you covered so many things, or rather everything. So yes, so it's very interesting that you highlighted that the importance of mechanical design.
Yeah.
And then selecting a control algorithm correctly as being fundamental. Now, there are many questions. Participants, if you have any questions, you can type in the question answer box. I do have many questions, but I will just ask a few. One question is that you talked about nature and balance.
Nature.
So what do you think about the future of balance?
Nature.
What I mean is that the human balance control system, for example, walking, running,
Right.
simply juggling an object.
Juggling.
No robot is as good as a human.
But
So
some
what?
point,
Yeah.
some point is robot can do better than human. Okay, there are depend on task. Okay, some part only human can do it, but some part robot can do better than human. Like inverted pendulum, like this. Okay, I cannot do it, but robot can do better than because my bandwidth is limited.
Yes.
I cannot move that fast, but robot can do it. So that it depending upon the task, we have to select a suitable system from design to control. About the nature, we human cannot control the nature. We are living with the nature. So the only thing we can do is that do not bother nature. Do not, we have to do we have to think about environment. That's my point about nature.
There are a few questions. We have maybe a few minutes. The first question is, can variable stiffness actuators play a role in balancing mechanism?
Variable stiffness role. I don't quite get it yet. I'm sorry.
Okay.
Can
you see the question on the right side Q&A?
Oh, right. Oh, I didn't know. Oh, can find this. Where I can see it?
Q&A.
Blue color message icon. Blue color message icon on the right side.
Chat.
Chat. Yes, chat.
Oh, chat. Okay.
Next to the chat, there is participant and Q&A. Top.
Oh, Q&A. Oh, okay. Oh, okay. Can variable stiffness actuator play a role in balancing mechanism? Variable stiffness actuator because different stiffness, okay, and play a role in. Yeah, of course. If you have a variable stiffness things, then it's a more advanced actuators, right? You can actually adapt to the change to the environment. Okay, single actuator with one stiffness can do only one things. Okay, but if you have some active control inside with the sensor measurement, those can be compensated by actively. So that variable stiffness actuator is a passive. I think to my knowledge, it can be considered as passive. Maybe you can add active control there. So the combination will give better performance. Not only one things. I don't know. Is that answer your question? I don't know. Yeah, of course, play a role. Yeah, play important role. But my point is that okay, you have passive mechanism there. Okay, not only the passive mechanism, you add active mechanism to improve or to satisfy performance. Those active mechanism requires sophisticated control algorithm to deal with uncertainty from internal and external. I'm sorry. Okay, that was the first question. And then second, can we use passive control method at actuator level to threshold the current as per identify system rather than using active sensor like force sensor? Oh, okay. So this one is that without using force sensor, okay, there is a approach of using a current sensor, measuring the current instead of force sensor. But it's a limitation. It has a limitation. The current sensor has accuracy is low. Okay, that compared with for the torque sensor, but your task is not require that accurate performance, then you may estimate current and use that as a force torque sensor instead. Okay, then you can save the money for force torque sensor. But recently, the force torque sensor, the cost is down. So long time ago, force torque sensor is very high. We cannot, afford that much. But now is the sensor price is, getting down. So it's trade-off, okay? So what kind of performance do you want, okay? Actually, and sophisticated performance you want, then I think you do better use the sensors there. And then, but certain performance you satisfy about the interaction, then you can estimate the current, use that as a disturbance to estimate force. Okay, so there is a depending upon application. Okay, how did we go about PI tuning? Yeah. See, in simulation, in the MATLAB control, you have the plan. Okay, number is fixed there. So PID gain is already, you can easily do. Okay, select optimal. Okay, but real system, if you make the system and then you apply the PID control there, it does not work that way. So from my experience, setting the PID control is kind of trial error basis. Okay, so that it takes many times, rigorous time to make it better. So in order to avoid that time, then you use intelligent control. Okay, the PID control is a primary. Like I showed the example, you add neural network to compensate those deviation by gain error, so that you can combine together to improve the performance. Okay. Also, the limitation of PID is that the nonlinear uncertainty. If your system has too much nonlinearity there, then PID has limitation of performance. So those limitations can be compensated by other mechanisms: time delayed control, disturbance observer, and intelligent control, sliding mode control, whatever. So that you have to pay to have better control algorithm. Okay. So PID tuning, like I said, it's there is no rule for that, because our system, the modeling, our system is very difficult. It's not single model. It has many models there. Okay. So one solution, maybe you can have a PID table, lookup table, so that different cases you can apply different gain to that. Okay. So extension of this lookup table is intelligent control, fuzzy control, neural network control, infinite lookup table. Okay. So another thing. So what was the software used for area manipulator simulation? Area manipulator simulation. We did not show simulation. We actually did actual experiment, area manipulator. So those area manipulator is experimental study. Okay, not the simulation. Okay, so is it possible to make accurate environment stiff? Yeah, using disturbance observed at some position sensor near the. Okay, good. Accurate environment stiffness. See, environment stiffness estimation is quite difficult. So that our approach is that not estimate environment stiffness accurately, but apply more advanced force control algorithm to take care of those uncertainties. So there's some of the force control algorithm here. I don't have much time to go through detail. I have proposed some impedance force control modified impedance control to track desired force there, is that hybrid force control does not require any information about environment, which is good. Impedance control actually originally from information about environment, stiffness, and environment position. So I published about the impedance force control algorithm without knowing environment position and environment stiffness. So that's what I published, back in PhD era, 20 more than 20 years. So the student, if the student is asking this question and look for that paper, then there is an algorithm about without knowing environment position and stiffness, so that we propose impedance control. So sometimes that algorithm, single algorithm cannot perform well, then you add another TDC neural network, so that later on we published combined with other algorithms to minimize error further. Okay, that was the my experience. How are you achieving the delayed acceleration data for your time delayed control? Delayed one, just the simple, you store, software, you can store, store the previous control input and use that previous, your command is a data, right? So that you store there, and then next sampling time you use that. That is one sample delay. Okay, which book would you recommend to learn control? And see, at the introduction, Professor Dorf write modern control system, which is kind of Bible of control system. I think that is very good about control system. So I studied that book, okay, from my beginning. All right. Okay, and then how are you applying neural control for bearing time? Bearing time delay. I think maybe this question is related with teleoperation control of haptic, the thing we hear. So at the time, we are actually controlling a mobile robot with the force sensor, and then we have controlling master as a haptic device through the internet. As you know, that internet is the time delay is not fixed; it's time varying. So that how can we solve that problem, time varying problem? So one approach we look for the literature is that to use the Smith predictor algorithm structure. So Smith predictor is actually the structure that the delay term at the when you have a transfer function denominator numerator, the delay term was in the denominator that caused instability. So when you use Smith predictor, that delay term out of denominator and go to the numerator, so that stability can be improved. That is the function of Smith predictor. So our goal at the time of using neural network is to replace Smith predictor, such that we do not know time delay, so that neural network actually replace nonlinear time varying time delay. That was our neural network control for time delay at the time. Okay, last question. Okay, what will be the load reinforcement control and dealing? Okay, very good. Yeah. Now one of my students is working on reinforcement control. Okay, so reinforcement control is a two phases. You have to do offline phase learning and do online. But here I'm presenting neural network control is purely online, without offline learning. So it's a different learning category. Okay, when you do neural network control here, it's a purely online. But reinforcement learning, you have to learn with data many times, so that you have to do offline first and then do online data. So I think that reinforcement learning control is powerful because it learns many things. Okay, all case of happening there, so that it can be used. So that real application is humanoid balancing control. Okay, based on reinforcement. Okay, so many different environment surface. The humanoid robot as walking there, falling down, and then use that data to train the robot many data and many times, so that successfully the working has been done. That's one of the example of reinforcement. I think the reinforcement learning is very powerful. Okay, because it has a lot of learning time with many data. So learning depends on data. If you have rich data, then learning will be better. If you have short data, then learning cannot be better. Okay, is it all questions I answered? I don't know.
Yes, your answers. Thank you. Let us thank Professor Seul Jung again
Okay.
for taking his
Thank you.
time. And
Thank you very much.
thank you. Thank you.
Thank you,
Professor Young.
yeah, Professor. Yeah, any
Yeah, can you come online now?
comment?
Yes.
Yeah.
Yes.
Yeah, actually, we are going a little late, so I'll.
Oh, this is late. I'm sorry. No. So, see, now my research, is improved by a lot of Indian, colleagues.
Thank you.
Yeah, Bibraj Sutta and
So,
Juba. Yeah.
Professor Young. So, as a prize, give 1 or 2 hardware to us to do some experiments.
Right. So, I didn't quite get you.
For the price of the Indian researchers you are hiring to do the good research, please share 1 or 2 of your hardware, maybe the drone or maybe the robot, to us to use it.
Yeah. Okay. I think they have, they learn, all the hardware. They use all the facility in our laboratory.
So we'll bring to India to use them.
Putting it over there. It's very difficult,
Okay. Yeah.
Anyway, somehow, we can collaborate. Okay.
Yes.
I get a lot of help from Indian colleagues.
Yes.
So then if we have anything we can help, then we can help. Okay. Yeah.
Assist to you.
Yeah. Okay. Thank you, Professor Jung.
Okay. Thank you, Professor.
For the great talk. Yeah.
Okay.
And
thank
so
you very
we
much.
move on to the next session. So as we are running a little late, and we have an industry session also, industry speaker. So what we'll do is in session number 7, we will start off with the industry talk because he has to leave at 11 o'clock. And then we'll move on to the paper presentation of 52, 22, and 69. Okay. So we'll start with the industry talk by Dr. Jagannath Raju of Systemantics, and then which will be followed by the 3 posters, 52, 22, and 69. Yeah, Rajiv, can we bring Dr. Raju on stage?
Yes, sir. I've added him.
Okay.
So there'll be 2 names. One of them will be from iPad, where he will switch on his video, and another will be the computer from where he will be sharing the screen.
Yeah, and the session chair for this session is Professor Subir Kumar Saha of IIT Delhi. So Professor Saha, please take over the session.
Well, welcome to this session. Thank you all the participants, and particularly the speaker, Dr. Jagannath Raju. And I met him first time 1990. I think he may remind me in a meeting of Robotic Society of Japan in University of Tokyo. The guy from MIT and planning to return to India. And 4 years after, suddenly I see him at IIT Madras, mechanical department, and came to know that he started the Systemantics India Limited. So I saluted him, how bold he was at 95 to start a company. Then later on, we had several interactions, and I am proud to say that I bought one of his first robot developed PPR, pick and place robot, which we have kept in our laboratory for many, many years. And I came to know that he has developed many, many new robots. I won't disclose the confidential item. Maybe he will share during the presentation. And maybe I will get one free from him, as a gift. Thank you, Jagannath. So, by the way, he's I Madras graduate, so and MIT PhD. So, hand over to you, Jagannath.
Thanks, Shubir. Can I be heard? People can
Yes.
hear me? And
Yes.
I'm trying to turn the video on from my other connection, but it is not allowing me.
Not sure, sir. Maybe I have given you full access.
From both the account, from
Yes.
both the...
Yeah, both are on the stage. So,
Okay. So I think we can actually go forward without the video if it doesn't come on.
But we don't see you either, actually. Acha, video is not working.
Yeah, 1 second. Cam
so
off.
can you try sharing the screen once, sir?
Yeah, let me just try sharing the screen. Share.
Yes, now PPT is visible.
Okay, I think I will spare people having to see me.
Okay, sir.
So let's go forward. Shubir,
Can you
you're
speak,
okay with
please?
that?
We'll try.
Yeah. Can people
We
hear
don't
me?
hear you, sir.
You don't hear me. Let me go back to the...
He
So
does
we
not
don't
require
hear you.
two. He does not require two. Maybe one would be sufficient, no? One.
No, the system on which he is presenting, he does not have a webcam, or maybe the
Okay.
mic also.
The mic is on. It shows me mic on.
Jagannath sir, Raju sir, I think you have to. Are
Let
you using
me...
same email ID for both the logins? If
Yes,
so, then
yeah.
we have issues.
Okay, let me just log off the other one.
You may stop sharing. At least we'll hear you.
Yeah, I've stopped sharing the other one. Now let me see. Can you hear me now?
Or what we can do is you can send me your slides. I'll present and you can speak if that is also okay.
No, my first question is, can I be heard?
Or Professor Ashish Datta also.
Because I was being heard earlier.
Yeah, now when you start sharing, we are not able to hear you.
Oh, I see. Okay.
So can you please email the slides or the PDF if it is okay?
Ashish, you have the copy with you? I can email to...
Yes, you can email to Professor Ashish.
He already has it from yesterday.
Yeah. So Rajiv, I'll send it to you in your account.
Sure, sir.
Hi, Rajiv. How are you doing?
I'm good, sir. Thank you. I'll just open my mail. So till it comes, you can just...
Yeah. So Ashish, Subir, Rajiv, all of you, thanks for inviting me back as a sponsor in the first place. I think this pandemic has resulted in a lot of innovation about how we get together. And I would have preferred actually to be back on, I think we have done the stuff at Delhi, then Madras, and Chennai, and then now Kanpur. I think, Rajiv, you're ready.
1 minute. I'll just open it.
So we have been trying to build robotic arms in India for the Indian small-scale industry for a very long time. I think even to date, I think most of you will be aware that there is no Indian manufacturer of robotic arms. In the last couple of years, a lot of things have changed in the sense that
Do you see this, sir?
yeah, I can see it, right? So
how come, sir? Can you hear me?
I can hear you.
Ashish, sir?
Jagannath,
Yeah, the minute you are sharing, I think it's going off.
How come I am sharing?
I've turned my iPad off, so now it no longer has anything to do with the iPad.
Dr. Raju, are you there?
Yes, I'm here.
he has blocked the sound.
No, that is showing only one Jagannath, Raju. The other one has been.
Yeah. Other one I've turned off.
Okay, let me turn my screen on. When we turn on my screen, we are losing you.
Correct. So there's
Are we in the
something with
same
the
table?
presentation.
No.
When the presentation comes on, you're losing
Raju,
me, right?
Are you there?
I'm here.
Oh.
Can you hear me now?
Yes, we can hear, but once I go to screen share, we are losing you. For some reason, this hasn't happened any time.
Right.
Let me just, I don't know. I'll move Sudhir sir downstage, if that helps.
Maybe it becomes another participant.
Okay, let me try sharing.
Down someone actually.
Yeah, there are only two now. Okay, I'll just
share again.
Yes, sir. Page width, fit width, fit height. 1 second, please. Put one full page. Okay, we'll try this.
Okay.
Can you speak?
Can you still hear me?
Hello, now you talk, Yuki?
Yeah, I am talking.
It's gone.
How is this happen? I mean, this doesn't happen.
There is a suggestion from somebody to make me the host and try. From Mr.
We can do that. We can make him host.
How? We haven't done that.
Manage remove from stage view profile. Mute.
No, that has to be done backend by the event managers.
Can we just call them up?
Yeah, I'll just.
And I have another word suggestion actually. First show the slides, 2 slides, then he talks. Another 2 slides he talks.
No, sir.
So without sharing screen, I can actually talk to the slides, but other people are not able to see it, right? That's the problem.
And that's why I said first show the 2-3 slides, and then you talk from the slides, so we have some idea what we saw, and then you tell the story, and then you show another 2.
No, just give us 1 minute or 2 minutes. We'll just see if we can make him host.
Sir, are you calling?
No, can you call? I'm not good.
Okay, I'll just.
Whom are you calling, Rajiv?
Toshi.
Okay, I have only Rajkumar's number.
I have her number. Or another option is, Dr. Raju, we can put you on speaker from mobile, and you'll be able to see the slides. And whatever you speak, we'll put it. That's okay?
But they will not be able to see the slides, right?
I will project. Only thing is they will not hear you from the computer, but they will be able to hear you from my speaker.
Hello, good morning. This is Santosh. Good morning, Santoshi, or somebody to help, because we are having a problem with the one of the speakers. Yeah. Yeah, they are coming. They are coming to help in a minute. So what we can do, we can make him host, and then we proceed.
No, I can give the introduction part of it. Doesn't really need the slide. The first couple of things, since I have access to it, you can listen to me, because the first two slides are, there's no real content that people have to look at. They can look at it later. Only from the third slide on, and the last slides is where I think it would be helpful.
Okay.
Does that work, Ashish?
Yeah, I think
Everybody can hear me now. Let me get started. Huh? We'll figure it out how to get this done. Okay, so as I was mentioning, we have been trying to build robotic arms for quite a long time. For the last 3-4 years, whenever we have had inquiries from industry, the first question they've asked me, sir, is your robotic arm a cobot? So I was intrigued why people were looking for cobots, and I would ask them, why are you looking for a cobot? They said, that is the future. So we are now, basically they were trying to future-proof themselves because people had said cobots are the future. And as most of you are aware, this is something that has sort of coalesced over the last 6-7 years. My understanding of collaborative robots many years ago was that there would be two robotic arms collaborating with each other to execute tasks. That whole thing changed, both with the introduction of Baxter by Rethink Robotics, who did a robot that they said you can have people working next to it. It will know of your presence, and then there won't be any safety hazard. Conventional robots have always been built for high productivity. High productivity means you need very fast motions. If you need fast motions, you need very high acceleration. If you need high acceleration, you need very stiff links, which means the links have to be made of steel. You need very high power motors to generate high acceleration so that you can build up to high speeds. That's been the conventional design of robotic arms. That introduced the safety aspects where if the robotic arm, heavy robotic arm moving at a very high speed could actually injure people if there was a collision, inadvertent. So people use safety fences to protect the humans in the workspace of the robot. That is the conventional one. The thinking behind what Rethink wanted to do and what Universal Robots came up with was really, you should have people working next to the robot and there should be no injury to them which is of any consequence, really. And the way to achieve that, they felt, was to reduce the speed of the robot. In a sense, saying that the robot momentum or kinetic energy should be such that in case there is a collision, the transfer of energy is very minimal. This essentially means that when you say collaborative robots for cobots, at the current level of cobots, you are not avoiding collision. You are saying, let us minimize the impact. And you can do it by reducing the inertial mass and limiting the speed of the thing. You also eliminate chances of injury by making sure the body geometry has no sharp features, everything is rounded, and you actively drain the energy from the system. At the next level, people are talking about saying the collaboration should be at the level where you avoid collision, which means it may be more expensive, but you may have to use vision, you may have to use many other kinds of higher bandwidth sensing systems to avoid, and in real time, the robot arm should be able to plan around the presence of the person and continue to work, is really where people would like to get to at some point. As a result of this, the design of the cobot means that now you have to use aluminum for all the robot components, including the frame, everything else. If it is an application where it's not cost sensitive, there are people that are already using very light carbon composite materials to achieve very lightweight. And the key to the selection of components is you need to be able to get the highest torque outputs per weight ratio, per weight of the two major components, which are the speed reducers, the gearboxes, and the motors. Those you have to go for components which give you, for a very low weight, a higher torque. The way the collision detection in cobots there used to be collision detection even in conventional robots by sensing motor current. But it was not very effective because motor current doesn't spike very much because the speed reducer attenuates the inertia from the output joint back to the motor shaft. And so you don't get the fidelity of motor current sensing is very poor. It's very low sensitivity. So that has never really worked well. What people who have started building robots like Universal and Rethink and everybody else, they decided, okay, what we should do is we should put two encoders, one at the motor shaft, one at the output of the speed reducer. The twist of the joint, which basically tells you if there was a disturbance, can be used to detect collision. And if you want something even with higher fidelity, you can put a torque sensor at each joint, which will tell you that there was a disturbance torque due to some collision. Or you can decide to put a multi-axis force torque sensor right at the tool frame. If it's at the tool frame, you will not get the same kind of fidelity as you will get if you were to put it at the joint torque sensor, because now you are introducing the stiffness of the links into your dynamics, and the fidelity of the signal will not be as good. As a result of this, the evolution of design for cobots has depended heavily on the evolution of the component technologies, because now you are saying all the components have to be such that they can cater to the design requirement of a cobot. So the first requirement was really that if you are going to make the cobot so that there are no external components, everything else, you have to have distributed control, because the harness now has to pass through each joint. So to have distributed control, what you will need is that every single component in the joint has to have a hollow bore. Now, distributed control by itself is not new. I think Subir will remember that what he mentioned, he bought our first SCARA robotic arm that we built in the year 2000. We already had distributed control in that product. And in fact, if you think about it, we had aluminum frames then, we had everything rounded. So in a sense, we had made a cobot at that point without thinking of it as a cobot, because it was, first of all, pretty small. So it never would have taken up that momentum. But we never tried to sacrifice speed at that point. We just kept the speed as it was. But it was not possible at that time to commercialize that, because a lot of the components that we needed were not hollow bore. So we had to do a very complex kind of design to get around the hollow bore requirement. That has changed now. Component technologies have reached the point where you have very lightweight speed reducers. I think many of you will be familiar with harmonic drives. They were under patent till early 2020, that is early last year. The patent ran out. So there are many, many manufacturers now, besides the original manufacturer, which was Harmonic Drive. They're all available at hollow bore. And the good thing is a lot of manufacturers are sticking to a very standard mounting interface, which means you have a very interchangeable design. You're not tied down to a single supplier. And pretty much the industry has now coalesced around 5 sizes of harmonic drives, which will define what is the kind of robotic arm you can actually build with the. I heard something.
Dr. Raju, we'll try one event person is joined. Let me try to share my screen. And Santoshi, whenever we try to share the screen, we are losing Dr. Jagannath Raju voice.
Audio is going up, right?
Yeah, I'll just try to share again. I'm using Chrome this time. Let me see if I can open Chrome tab. Okay, do we hear you now?
Can you hear me still? I'm speaking.
Dr. Raju, can you please speak?
I'm speaking.
No, he's being lost again.
Yeah.
Santoshi? He has joined from iPad. Is that an issue?
No. iPad is out
could
of the
be
equation.
an issue. So can he use Google? Which browser is he using?
He is using iPad and Google Chrome.
No.
iPad itself, kind of throws errors. So, is there any other device that he can use?
Can you
I'm not sure. We'll have to stop and then.
stop? No, correction. I'm not using the iPad. I've turned it off. The
Okay.
iPad is not there. I'm using Chrome on a Windows desktop.
Okay.
Sir, can you hard refresh? Rajiv sir, while you're sharing the screen,
Right.
Jagannath sir, please hard refresh. That is Control plus Shift plus R.
Okay.
Rajiv sir, can you share your screen?
Okay,
Yes.
let me try sharing screen. Share. Now I'm sharing.
It says Jagannath screen.
Right. I'm sharing my screen now.
He also started sharing the screen.
Yeah.
Okay. Or maybe because
Two
he
screen shares were there. Can you stop, Rajiv sir? Yeah.
But we don't hear him. That is the problem. When he shares the screen, we can hear
You
him.
want me to share or you want to?
I want Rajiv sir to share the screen.
Okay, I'm going to share again.
Yeah.
Let me share.
No, not you, sir. Rajiv sir should share the screen.
I shall share the screen. You just use
SK
Control
Saha sir,
Shift
you're
R.
on mute. If you're trying to talk, if you're on mute, you're on mute. Okay, who shared the screen now?
He only shared. I think he did not get what we were telling. Dr. Raju, can you stop share? No, then
he share if he can do.
We can't
No,
hear
sir,
him.
please don't share the screen. Stop the screen. Stop sharing the screen.
I've stopped sharing. I can hear you.
Rajiv sir, you share the screen.
Rajiv Lochana will share.
Now, Jagannath sir, can you hard refresh? That is Control plus Shift plus R.
Control plus Shift.
Okay, he left and he should join now. Earlier he had joined from iPad, so now he's joining from a desktop.
Okay, he has joined.
We still can't hear him. Dr. Raju, we can't hear you.
I've turned the mic on now.
I don't think he has hard refreshed, because if he hard refresh, he'll just go off the platform. He has to tell him that he has to click on Control Shift R. Since he said he's not using iPad, he has to click on Control Shift R. When he do that, he'll be out of this website and he'll come back again. Yes.
Dr. Raju, please do Control Shift R. It's a hard refresh. I have hard refresh. That is what he's sharing.
Yeah. Please look at the chat box.
No, he didn't do that.
Yesterday, a few people tried that. They also again came back on stage.
Yeah.
Why don't you log him out? Maybe whatever Santoshi or Rajiv. Can you log him out and then?
Sir, I think we'll do one thing. I'll call him on WhatsApp. I'll put him on speaker. Whatever he says, at least let us proceed ahead then.
Yes, I think that is the only way out. Yeah, let's do that. Keep the speaker in front of the mic, your mic, and that should be enough.
Systemantics. Sir, I don't have his number. Ashish, sir, can you?
Okay, yeah, I'll just call him.
Yeah. Dr. Raju, Ashish Datta, sir, will be calling you. He will be putting his phone on speaker. Sorry, this is unexpected. We were not sure.
Jagannath, sir, if you did go off, when you come, the one who has to bring you onto the stage. Without we bringing you onto the stage, you will not appear attendees in the attendees on stage.
Actually, Santosh, yesterday also something like this happened. So probably after hard refresh, they end up on stage. Maybe.
Yes, it comes
Let's
back.
just proceed ahead.
No, actually, that's not possible.
Okay, no problem. We'll just go ahead in this interest of time.
Or else, Jagannath sir, can you click on the refresh button that is on the top next to the event link?
Browser.
Yeah, now he went off. You see, now he's not there in the attendees on stage.
Okay, let's hope that.
No, he will go out, and when he comes back, he automatically comes back on stage. That is what
No,
happened
no, no.
yesterday.
He won't come back automatically on stage. He will be,
Okay, he's come. Okay, we can bring him on. No,
okay,
he's on
now
stage.
he is on stage. Now, Jagannath sir, can you click on Control plus Shift plus R?
Can you hear me right now? You can't hear me right now.
Yeah, now he went off stage.
There is something else shown now. Presentation on the left side.
Okay, so what I'll do is I'll just call him.
Yes, sir.
Can we ask him to try to use the link in incognito mode?
Yeah, so what we'll do is I'll put you on speaker on the phone. You can speak on this. Can you see the slide?
Yeah, I can see this.
Oh, okay, so what we'll do is I'll just put you on my speaker phone and I'll connect it to my mic. So I think it should go through. Hello, yeah.
Yeah, sir, can you close this window that you're in right now and open an incognito tab? I hope you're, just to be on the same
Santoshi,
page.
I think it's okay. We'll manage because now we are already late. We'll just proceed ahead.
Yeah,
We can
so
see the
Dr.
slides. We can speak.
Yeah, Dr. Raju,
Okay,
you can
sure.
hear us, right? Okay, I think when he speaks, we can hear also, right?
We are not hearing. We are not hearing. You are putting it there.
Your mic has to be in front of the mobile
Your
mic.
mobile has to be on speaker and your hands free.
Hello?
Hear me now?
Yes.
Yeah,
Okay.
I think we can hear you.
Okay, so I've got the mic on the computer, right? So let's go ahead and you can hear me. Correct?
Yes, yes.
Okay. Let's go.
Yeah. Now
Okay, so I'll need somebody to scroll the screen. Okay, so I've covered this. This is where I am. No, go back. That's it. Okay, let's proceed. Okay. So as I was mentioning, it's the lightweight speed reducers that are very critical components and are actually available from a lot of people. Now, there is an echo that I'm trying to get. Okay, let's continue. So you will find a lot of the cobots that are available now are all very similar because everything is based on the same set of 5 universal sizes of harmonic speed reducers that everybody is using. The second critical component is that we need hollow bore frameless BLDC motors also. So that's the second. This also has been a problem that people were not able to find this kind of motors. Now, as I mentioned, everything has to be hollow bore. So even the encoders that we need would have to be hollow bore ring type of encoders. Fortunately, magnetic encoders are now evolved into models which are very rugged, have very high resolution, and are also absolute encoders. So that also exists. And we have had to build custom sensor modules for these so that they would fit in the space that we need. And at the last component that you need is a hollow bore brake. Unfortunately, you can never find components which are exactly the geometry that you need. So these also a lot of times have to be custom built. So these are the very critical components that would be used in any cobot arm design. Next slide, please. So using this, about 2 years ago, we started designing and building cobot arms. We had to stop on the first wave. The first wave came when we just started doing the proof of concepts. We completed that and started actually manufacturing the joints of these robots. And then the second wave hit about 2-3 months ago. So we just came back to it about 3-4 weeks ago. But we are now in production of these joints. And our portfolio now has 3 sizes of robotic arms, cobots, which you will see will reflect, as I mentioned, almost everybody else's portfolio. You will find one which is 3 kg at about 600 millimeters, etc., etc. And there are 3 of them. Let's go to the next slide. So the critical component that we have designed is what we are calling an integrated dual actuator. So these are come in 5 sizes. We have integrated everything into an aluminum frame using encoders both at the motor and the joint so that we can detect collisions. We have a through bore right through, so we can actually take the harness through it. We have designed and built our own holding brakes to match the rest of the components. So as you see in the bottom right-hand corner, these are the L joints that are currently in production. We are making 5 sizes, 14, 17, 20, and 25 are in production. 32 is in progress still, which means we are ready to release both the model, which is a 3 kg payload, and the 5 kg payload. They use the first 4 sizes of these actuator joints. You can go to the next slide. Now, this is a very busy slide, but at the end of the day, what has made Universal successful is that they made it very easy to integrate into what anybody wants to do with the robot. And especially if used to small-scale industries where they cannot afford to hire very high-skilled resources to program robots and do all these things. Right. So I've just listed here. People can look at it at their leisure. You can easily integrate into the cloud. You can integrate into ROS if you are in OEM academia. You can use your own open source libraries. We have done a lot of proprietary motion planning and control, which we are happy to open source into academia so that you can use those up. Most of that we have listed is already implemented. Some of it is in progress. What you see on the right-hand side, everything in green is something that we have done and tested. Everything in blue background is stuff that we are in progress. And everything in red is something that we're going to take up as soon as we are ready with everything. So we're going to give you integration into those things. So this pretty much covers where we are right now. Next slide. For production and sales, we are registered on the GEMS portal. You will see this is a constraint for many purchasers in government institutions, so we have done that. We are still having a problem on the portal in uploading the data sheets. Right. The 3 kg model is in production and we are accepting orders. The model for the academics can be given at a lower cost because some of the features are for industrial use and we can strip them out if you don't need them. This will be in addition to an academic discount. And as we said, we'll open source the proprietary code for using for research. And one of the things that I've been told is the last mile, which is the gripper. There are no electric grippers that are available easily. So we are designing and building one. And we are offering it as an incentive for anybody who wants to place an order before the end of the month. We are happy to include that. And we hope to have the 5C up and available for ordering in August, in the next month. And as I said, the largest joint, which is we are finishing the design, that will be for the 10C, will be available a month after that. So we are keeping our fingers crossed that even if there's a third wave, it will be much lesser intensity, and we can finally get these things off the ground. I'm happy to take any question.
Yeah, thank you, Dr. Raju. Is Professor Saha there?
Hello. So thank you, Raju. With a lot of finally we could make it up. So other
yeah, I know. The thing of you'll always remain our first client, and as soon as things come back to normal, we'll definitely consider. You've earned a model, but we have to get ourselves out of the economic impact that all of us have felt.
No problem.
Especially small
we have now we have a big company owned by IIT Delhi, so no issues. You can put 2-3 of those. We could afford now easily.
Yeah,
we have 170 crores in our hand.
But you'll have to buy those.
Yeah, that's what I'm saying, buying, right? And then we'll rent it out to other people, to earn money. Just a joke. Okay, so questions, more serious business. Questions by the participants.
I'm looking at the Q&A.
Yeah, please.
It's not updated from the previous speaker, I think.
Okay, here is one. I think, how are you achieving the delayed? Okay, yeah.
So can
let me ask. Yeah, please go ahead, Raju.
Yes, sir. Dr. Raju, the last 3 axes are usually intersecting in case of a wrist partitioned robot. In case of universal robot, and also in your model, the last 3 axes are not intersecting.
Yeah.
Can you please throw some light on that?
It's not an issue anymore because you don't need a closed loop solution given the computing power you have. In fact, if you look at our other model of a hybrid kinematic arm, we are actually doing the entire inverse kinematics of this in an iterative solution at absolutely incredible speeds. That used to be a problem only when computing power was not there.
Okay.
So there is a question.
Sorry. Yes, sir. Continue, sir.
You finish, Rajiv.
No, like, do you still have analytical formulation, or you look at numerical methods, like as you said, iterative?
It's a combination of the two, because the small offset doesn't require. It's only iteration of small iteration. It's not iteration having a forward kinematics and then trying to iterate on all the frame transformations. It's iterating on a single parameter.
Okay, so we have a question here. Can you please throw some light on harmonic drives? Did you build all that or bought over?
We first sourced harmonic drive kits about 5-6 years ago from Harmonic Drive of Germany, very expensive. We built the hub sinks and everything. The precision had to be so high that we found that we were getting a very fine oscillation on it, harmonic oscillations on it, in addition to the thing. And the price point was not affordable to meet the price point that we wanted for the robot. So we had to go away from that. We tried building our own speed reducers, which are not harmonic drive, and we're not very successful at it because this weight to torque ratio is a very difficult thing to achieve with other kind of speed reducers. So right now we are buying completely assembled units, but they're available from at least 10 suppliers, which all have the same geometric interfaces. As an add-on to that, there is a company now in Ahmedabad which is which is in touch with us, saying that they are building harmonic drives. But they're not hollow board as of yet.
Okay, so we'll take one more question because we're running really late. What kind of control you implemented on your arm?
I can see that. So,
oh, okay, you can see that. Okay.
So once you have very high gear ratio, PID control is more than sufficient. But what we have done is we have also added gain schedule, so that during servoing, during the tracking phase, you can have one set of gain. During a regulatory phase, when the motion is done and you are holding at some point, you can use a second set of regulatory gains, because you don't want to have very high integral gain during the servoing, right? And then we provide a third set of auxiliary gains if you want to do something in addition to servoing and regulating for any reason. The second thing we have implemented, now that we have two encoders, one at the joint and one at the motor, we are also doing dual encoder control, so that you are actually also compensating for the stiffness of the harmonic drive. So both of those are implemented.
Okay, so Bibraj, please excuse us. As a chair, I have a liberty to ask one question at least.
Right. I'll just finish with the question. He said, how about the backlash and the actuate? It's more wind-up stiffness than backlash. And that can be addressed with the dual encoder design. Okay, Subir, your turn.
Yeah. So what are the price ranges you are keeping it? Like the 3 kilo payload, what is the target price?
For the 3 kg model, its published price is 8 lakhs. You will see it on the GEMS portal. We are aiming for a target price of 7 lakhs for the academic community, where we strip off a couple of things which are not useful to the academic community. And when we get to the 5 kg model, we are targeting a published price of about 11 lakhs. About a 2 to 3 lakh price difference. It will be a 2 to 3 lakh price difference as you move up the ladder from 3 kg to 5 kg to 10 kg.
So I think, thank you, Jagannath Raju, Dr. Jagannath Raju, for the nice, and I know this is one of the probably the best company who have started designing from the scratch in India, and I wish you all the best. And thank you very much for coming here. Thank you, Jagannath.
Thanks, Subir. Thanks, Ashish, and thanks, Rajiv. Thanks for all of you who have signed on.
Okay, so Ashish, please guide me to go on to the next. 11:30, I wanted to leave also.
Yeah, there are 3 papers. Sorry, short presentations of 7 minutes each. So you'll be able to take them, all 3 of them?
Yeah, I think if you say 7 minutes each, I think I'll be able to manage, right? By 11:30.
Another 20. Yeah, another 20. Yeah. So Rajiv, please bring them on stage. Yeah, and Rajiv, I have to go at 11:15 for half an hour. So after this session, Sudhir will be there, right?
Okay.
AP Sudhir is there. Yeah. Okay.
I'll just add him now itself.
Yeah. So we have the next session, which is a continuation of the poster presentation from yesterday. So there are presenters for paper ID 66, 81, and
52, 22,
52, 22, 69.
Yeah, sorry, 52, 22, 69. Okay. So like yesterday,
am I audible, sir?
Yeah.
Just hold on.
Yeah. This is Lalit, sir.
Yeah.
Yeah.
Okay.
Hold on, Lalit.
So,
yeah.
Yeah, so you're audible.
Yeah,
so
actually,
like
it's a small request, sir. Actually, right now I'm in a function, so if possible, can you arrange that first priority of my this presentation?
What is your name?
Lalit, sir.
Right?
Lalit.
Okay, I think you can go first then. Yeah, but all the speakers, please restrict your presentation to 7 minutes. Okay, and after that, you can go to the floor area in the lunchtime, and if there are further questions, it can be taken there. Okay, so I think we can start off with Lalit.
Sorry, Ashish, so what is my role there? What am I supposed to do?
You're supposed to conduct the papers, yeah, and maybe ask one question at the end of the presentation.
Now we say
Yeah,
lunch
thank you, sir.
hour,
Am I
so I
audible?
was getting worried. Yeah. Okay, go ahead, please.
Yeah. Thank you very much, sir. Yeah, so this is Lalit, sir, from Visit Mumbai, and actually, our research is going on in the field of safety. Now, before coming to the actual topic, what research motivation we have, and actually why we have shifted towards this. So the thing is what actually currently government of India has already announced that the national electric vehicle policy, which will be implemented from 2020 itself. Okay, and the lot of efforts have taken by the government, and if you see on the road the number of electric vehicles are there, है ना? So because of this electric vehicle, although it is beneficial to the atmosphere, there are certain limitation of these electric vehicles, and we have studied that limitation to what points that should be developed in the electric vehicle so that there will be benefits for society. So the first thing is that because of the low noise and quick running operation of this electric vehicle, the pedestrians who are just moving on the road, they are unable to identify the presence of this electric vehicle. And because of this, many times the number of cases have been reported that because of this, some small kind of accident took place. So this is the first. Second thing is because of this say silent nature, many times driver used to sleep, that drowsiness, or you can say that because of this silent nature, the atmosphere is like this ki after certain period of time the drivers feel the much more comfort, and he may get for sleepiness. Okay, so that's what we try to do this. We try to analyze these two factor in our research, and basically first we have thrown the focus on enhancing the safety for electric vehicle drivers through vision oriented monitoring system. So what we did here, please go to the next slide. Yeah. So what we did in this, we have highlighted the focus on the past literature, ki what efforts the past authors have taken, past researchers have taken, and based on that, we have developed a model that if you implement that model in the electric vehicle, running electric vehicle, then definitely that will help to boost the safety for electric vehicles. Okay. So basically, throwing the focus on literature review, Jua et al. Have used the EEG, EOG signal using GN and LSTM network, and based on this, almost 98% for classifying endpoints of alpha waves under Leuven subjected cross validation, and they have developed this Grossness model. Then,
Mr. Lalit, see, you have only 5 minutes or 7 minutes
yeah,
maximum. Okay,
yeah, sir.
please save your
Please
time
go to
for
the
your
next slide.
important.
Yeah. So this is what the literature review. Yeah. So the objective is what, as I told, difficult for pedestrians. So based on that, we did the survey in the last year, and because of the this some lockdown that has been extended, so completely entirely for 1 year, the research has been conducted based on this. So we found out that most of pedestrians as well as drivers feel relaxed and they causes sleepiness. So this is the problem faced, and we identify that. The second is WHO that recommend that, or WHO stated that 1.35 millions of road traffic deaths have been reported. At the same time, electric vehicles are emerging on the road because of this government policy. So because of this, we have developed that model, and these are the some research objective. So very first, to develop the smart drivers behavior monitor model to enhance the safety, and second, to enhance the performance and feasibility of real-time driving situation. Please go to the next slide. Yeah. So methodology, what we did, we selected the Python language as it is open access language, and it is freely available. So in that case, what we did, using the OpenCV platform, already pre-trained classifiers already we are having, so we selected that. So based on that, we have prepared the data set for drowsiness detection, and what we did, we set a webcam to monitor continuously the behavior of this driver, and afterwards what we did, Using that, we try to analyze, yes, the model which we develop, whether it is working properly or not. Yeah. So in order to test the real-time condition, we develop the test rig. You can observe in the figure 2. Yeah. So in the figure 2, it's a layout. Yeah. And yeah, please. So here you can see that in this, in order to get the actual real-time environment, we have used certain component like three-phase induction motor for getting the sharp power. Then we are having this flywheel to getting the momentum, actual momentum. So likewise, we develop this model. Please go to the next. Yeah. And we try to identify the behavior based on this webcam. Yeah. So if you see the first two figures, so in that case, normal drivers Dawson's behavior is not reported. See that the close eye score is very less than 15, and if it is goes on increasing, then drivers, if the eye closing gets detected, then automatically with the help of relays we use the extended pedal for our braking set, and automatically brake gets actuated with the help of this automated system. And at the same time, indicators have been used to identify the actual the presence of this vehicle. Yeah. So that's what we try to find out in our first part of the research. Second part is going on. So yeah, this is what our first part of this the result. Please go to the conclusion. Yeah. So this is what discussion and conclusion. I try to club this because of this limitation of this slide as well as time. Yeah. So the phase area detection produces the excellent result, and it can be used for any electric vehicle. Yeah, and the model is having the around cost of say 25,000. So if government is enforcing to adopt this, so definitely this will help. Definitely this will help to use this. The second thing is that using this deep learning analysis, we are having the yawn detection and say driver documents can be recognized, and we are having the real-time car environment. In that you can use you can test the actual that feasibility of this system, so we check that performance. And the only thing is that that your face should not be covered by any mask or say anything. We are working on this again for increasing the feasibility or increasing the performance of this. And the last face detection avoid the unwanted fatal and incident. So that's what all about the increase in safety for our automobile electric vehicle purpose. So that's all, sir. Yeah, thank you.
Okay, thank you, Lalit. So how many tests you have conducted so far?
Yeah, sir. So for checking the feasibility, what we did, around 10 peoples of different ages, we try to cover the all, you can say that the test, and based on that, we found that whatever the result we got, although it is having the age less than 15 years, so again in that case also it works well.
How do you decide the success of a detection actually? You know, when do you decide success, when you decide failure?
Yeah, so we develop the test rig, and once the driver's drowsiness has been detected, so based on this,
That is exactly the question. That is the question. How do you define the drowsiness actually?
Using the eye blink, sir.
So what is the what is eye blink rate which you capture actually?
I'm not getting, sir. Means
what is the frequency of the eye blink which will tell that if it falls below this, then I'll call it drowsy? All right.
So it was around, sir, is what we consider that around 45. If it below the 45 tons, then drowsiness can be proportionately, you can call
45
it as
tons. 45 tons in 1 hour, 1 minute, 1 second.
1 minute, sir. 1 minute.
Okay, so thank you very much. So yeah,
yes, sir,
so yeah, give a hand for him. Next.
Thank you, sir. Thank you very much, sir.
Yeah.
Yeah. Thank you.
Next is what, Akash?
Yes, sir. We have Akarsh.
Yeah, Akash. Yeah, please start. Your time starts now. Yes.
Okay. So good morning, all of you. I am Akash, and I recently graduated from NIT Nagpur, and my research interests are controls, planning, and autonomous vehicles. So my research paper is Adaptive Look at Distance for Pure Pursuit Controller with Deep Reinforcement Learning Techniques for Autonomous Vehicles. So the trajectory generator and motion planner depends on various conditions like road curvature, static and dynamic obstacles.
Can you make it best 8?
Sorry, sir?
Professor Datta, can you please put yourself on mute?
Yeah. So
no, normalization I think you'll have to do because there is.
Okay, you continue. I'll just call him.
Okay. So so it depends on passenger comfort and road conditions. So it is the responsibility of geometric lateral controller, such as longitudinal and lateral controller, to mimic the path as close as possible of the path planned by motion planner. So in this paper, we used PID controller for longitudinal control and the pure pursuit control.
There is variation in every.
And we used deep reinforcement learning technique, DDPG, to tune the look-ahead distance of pure pursuit control.
Unless you normalize group-wise, they will not be normalized.
On the screen is the literature review. Is it fine?
Yes, please continue.
Yeah. So the longitudinal controller takes care of acceleration and deceleration of vehicle, while the lateral controller takes care of steering angles. So the existing lateral controller methods possess some drawbacks. Like the PID is difficult to tune in real-time scenario, and the optimal control methods such as LQR, ILQR, MPC, although they develop as motion planner and controller itself, but they have high computational complexity. So they can't be used in real-time scenarios. And the classical RL methods, they consume huge memory, and they are not quite practical to use in autonomous driving scenario. So we aim to minimize the cross-track and along-track errors along the path. That is, we want to mimic the path planned by motion planner as close as possible. So we use DDPG, Deep Deterministic Policy Gradient, which is an off-policy, model-free, actor-critic-based algorithm. In that, the actor decides the action and critic tells the actor that how good the action was. And we tuned the look-ahead distance of pure pursuit controller using DDPG. We also want to maximize the rewards of RL to ensure maximum steering aggressiveness and better ride control. So we used Carla simulation environment for our experiment, and the waypoints generated in Carla environment are fed to DDPG. The DDPG then performs. DDPG has two neural networks.
You have everything, na? You have the Excel file.
Like the critic.
No,
like the 1 minute. Ashish, sorry. Ashish, can you mute, please?
He probably is not listening to
us.
Hello,
Ashish. Yeah, go ahead.
Yeah. So the road waypoints are fed to DDPG. The DDPG has two neural networks: the actor neural network and critic neural network. The critic and actor neural network are trained along the course of time, and they perform the action, and that is fed to the vehicle model. The vehicle model tells that how good the action was, and thus the process continues. On the right, you can see there is a general workflow of our control process. Initially, the vehicle state were initialized. The vehicle states were X coordinate, Y coordinate, yaw angle, and the speed of the vehicle. Then, according to the state, the waypoints corresponding to the state were found out, and then using DDPG, the action was taken. So the action in this case was look ahead distance, which is the parameter of the pure pursuit controller. Using that, we can control the steering of our vehicle. Then we can estimate the rewards. The rewards methodology I will be showing in some time. Then after that, the Q values were stored in buffer. And if the buffer size exceeds the best, if the buffer size is less than the best size, the agent is updated. Otherwise, the values keep on adding to the buffer. So I mean by agent updation is that the actor and critic neural networks are updated, and so on. This process continues. So according to the rewards methodology, if the car doesn't collide throughout the episode, the rewards were -1000 into magnitude of cross-track error. If the car collides throughout anywhere in the episode, we penalized heavily with negative rewards. And if the car doesn't collide and it has cross-track error less than 0.05 for the whole episode, it has rewards plus 1000. So we performed 3 experiments. Firstly, we kept the speed constant, and we found out, as you can see on the top left, we found out that the rewards source increased. And in the second experiment, we compared our controller with the simple purpose controller with constant lookahead distance. As you can see, the cross-track error of our proposed controller is always less than the simple purpose controller. That shows that it is necessary for lookahead distance to change according to the road conditions. In the third experiment, we varied our speeds, and we found out that still the rewards were converged. And in the last graph, you can see the look-ahead distance keeps on changing throughout the episode. So the frames determined is so they are approximately 250 frames in single episode, and you can see the look-ahead distance is kept on changing throughout the episode. So I conclude that our paper proposes a novel lateral controller using DDPG to find the pure pursuit look-ahead distance. We performed 3 experiments to check the authenticity of our controller. In future, we will try to integrate our controller with motion planner, and we are doing the experiments with the existing motion planner of the ROS. So we will try to implement our controller in difficult driving scenarios such as low visibility driving, ramp, merge, overtaking. We will also try to implement our techniques into other other techniques such as LQ or MPC, because they have a benefit to develop as motion planners. So we can use a single neural network to train for the motion planning task and control task. And finally, we will also try to implement our controller in different time models and complex vehicle models. So thank you.
Thank you, Akash. So did you test it on a real vehicle?
Yes.
Did you test it on a real vehicle? This is for autonomous driving car, right?
Yes, sir. Sir, actually, we were performing the experiments on simulation first. Then we will be trying to implement on the real vehicle, but due to pandemic, we couldn't arrange the resources.
Do you have a real vehicle? Do you have a real vehicle car at VNIT?
Yeah, we have the real vehicle car, but actually we have all the sensors equipped to that vehicle, and just we are good to just put our algorithms into that. But due to pandemic, we couldn't just test it on the real vehicle.
Okay, thank you, Akash. So thank you very much.
Thank you.
The hands to him. Okay, next we'll move on to Professor Nayan Kakoti, please.
Is my screen visible, sir?
Yes, yes.
Okay. Very good morning and good afternoon to all. I am Nayan Kakoti, going to present the paper entitled Development of a Technology Education Program based on self-driven, self-learning and self-evaluating approach on behalf of my co-authors Janupriya, Abhijit, Rajiv Bhushan and Subir Kumar Saha. So to start with, robotic competitions are held all around the globe to provide opportunity to the students to design, build, and demonstrate the robots. The students are benefited from such competitions as it allows them to apply their theoretical knowledge while building a device to deal with the real-world problems. But in spite of such numerous efforts for making students equipped with these technical skills, the National Employability Report, that is the Engineers Annual Report 2019, stated that 80% of Indian engineering graduates are not employable. So to address this issue, a technology education program, that is RoboAnalyzer based online competition, has been proposed, and this program is for the students and faculty members interested in robotics. The objectives of this program is to enable the young minds to learn how to think and implement the innovative solutions to technical problems. So this ROC is basically based on an S3 approach, which is self-driven, self-learning, and self-evaluating. The ROC emphasizes that participants will acquire the skills of developing thought process for addressing a technical problem, while working in groups with people from different parts of the country. Importance for impressive presentations during the evaluation aims to develop the confidence and capability for public speaking. And the final objectives of ROC is to enhance the participants' qualities for becoming industry ready. So this slide shows some of the participants' activities being accomplished in ROC 2020. The work carried out for the participants was varied from writing their names using the trace of an NF vector in the virtual robot in Robot Analyzer, wherein these participants have been introduced to the different modules of the robots and the basics of the robotics. But as an outcome of their activities, we could see that they have used different concepts, like the mathematical concepts lying behind these activities, as well as using different tools like the CAD tools or the digitizer tools for accomplishing their activities. So these activities are being stored in two websites, in the Robot Analyzer website and Embedded System and Robotics Lab website, as shown here. So this is the website where we keep all the activities of the students performed during their participations. And this is one of the examples of the activities that is carried out by the participants. So where the participants go beyond the assigned task and try to implement some more activities doing frame digitizers as well as using some CAD tools. So to save time, I'll go and skip here and so the map on the right shows the participations from different parts of the country. Following the ROC 2020, where the 44 participants have taken part, in 2021, we have around 140 participants taking part in this activities. So the outcomes of this ROC was revealed in terms of enabling the participants to enhance their abilities in terms of like leadership, teamwork, peer evaluation, respect for the diversity and multiculturalism, which is one of the very important parameters in our education, then organizational and planning. The participants' works has been recorded in online platforms, that is in the websites of Robot Analyzer and the Embedded System and Robotics Lab of Tezpur University, that would help the interviewers to judge the participants' abilities for specific job profiles instead of evaluating them on the basis of a single certificate. So the feedback of ROC 2020 were considered for the second edition of the ROC, and the title of the program was modified as Robot Analyzer based online competition as Virtual Summer Internship 2021. We acknowledge the supports received from all the participants for their sincere and active participation in ROC 2020, and anticipate that in coming years we will be able to do more justice with imparting the skills for improving the employability of the Indian engineers. Thank you.
Thank you, Nayan. Since I'm the co-author of this thing, I might let Ashish to ask question, or I have a general suggestion. Yeah, Ashish,
okay,
go ahead.
I'll just. So it's a very nice initiative where people are learning. You know, people who cannot afford to buy a robot and do training, they can learn online. My only suggestion here would be that when we are saying we're imparting education or somebody is enhancing their skills, can we look at metrics of some kind of metric by which you can say that this is really helping? How do you know? In education, when you're teaching small kids, for example, dyslexic children, there are metrics which are before training, after training, how has it helped? If you could come up with, I'm not sure if there are metrics. If there aren't, maybe if you can make some metric, and then we can justify by numbers that, okay, this is helping. Otherwise, it is just English by saying that it has helped. Right? That is my only suggestion.
Yeah. Thank you, sir.
Great initiative.
Some
no,
rubrics we will be coming up with.
Yeah, I think let us do that analysis by ourselves. Yeah. Okay, so thank you all the speakers for all the three presentations. Two are on related to the vehicle side and one the education. So thanks all the speakers for the time and effort and presentation. So thank you. I'm done. Hand over to the organizer.
Thank you, Professor Saha, for chairing this session. Now I'm adding the speakers for the next session. Professor Datta, are you there? Okay, so the session chair for technical session number 8, which is on biomimetic and computer vision, is Professor A.P. Sudhir from NIT Calicut. He is a faculty in the Department of Mechanical Engineering there. Sudhir, sir.
Hello.
The general instructions for all the presenters is like we have 14 minutes presentation followed by 3 to 4 minutes of question answers and 2 to 3 minutes of changeover. So since we are running around 40 minutes late, we'll still be able to cover up. So we'll go as per the schedule, and we'll have an offset in the lunch break, maybe 20 minutes late. We'll try to have it. So effectively 11:40 is the starting time, sir. 11:35, you can please start.
Okay.
So I'll leave Rajiv and nice to see you, Sudhir. Please go ahead.
Thank you, sir.
Bye.
So
first, I think you're invited all the participants, right?
Yes, I have added all. There's one Dr. Deep Narayan Ray for last paper. I think he'll join later. Otherwise, other people are already here.
So I can start, right?
Yes, sir.
Professor Raju?
Yes.
Okay. So welcome you all this technical session 8. The first presenter is Hemkar Sharma. The title is Analysis of fiber reinforced soft bending actuators on various parameters for hand rehabilitation. So we'll be getting 14 minutes and maximum 3 minutes for the questionnaire session. Okay?
Okay, sir.
Okay, start present.
Yes, sir. I am Sharma with my professor Dr. Arokya Selva Kumar from VIT Institute of Technology, Chennai. I am presenting my paper analysis of fiber reinforced soft bending actuators on various parameters for hand rehabilitation. So the motivation for the paper was nowadays the hand rehabilitation devices that are used are really costly and are slow. And as there are mostly hard robots, so they are susceptible to harm the patient. Whereas they also need constant therapists with a professional to use the robots. Whereas these robots are very rigid, so they cannot be easily customized to every patient needs. So there is a need of new, better, and use and a rehabilitation device that can be used anywhere, as patients also need rigorous rehabilitation, which can be done like during the day, not only during the session, so that they can get well soon. So the problem statement objectives are like nowadays there are over 13.7 million new strokes of all types each year. Globally, every fourth person aged over 25 years will suffer a stroke in their lifetime. Stroke is second leading cause of death, whereas stroke is cause of leading long-term disabilities, which we are trying to lower down by giving cheaper, better, and regular rehabilitation device that can be used by a patient. So common type of rehabilitation methods are like power grip, pinch, thumb extension, table roll, finger flexion, thumb roll, finger squeeze, and thumb opposition. So these type of exercises are also difficult with the normal type of robotic actuator. Whereas if we can develop some soft robotic actuators that can help in doing these type of exercises with not mainly completely making the patient do this, but assisting the patient to work on these, on all of these or some of the exercises. So the main area of research was actuator design. So our actuator that we are using for the finite element analysis has a core mold. This core mold is made of elastomer. So in our paper, we are using two types of elastomer, different material properties to evaluate which one is better. We have chosen our materials from previous papers and some other papers that use same materials, and we have compared all three. Then we add a strain layer at the bottom of the elastomeric mold, core mold, to only constrain the motion of the actuator in only one direction. Whereas if we don't add the strain layer, it may only do extension, and it won't show the bending of the actuator. Then for specific amount of bending, we add a wrapping layer on the actuator. So how does this wrapping layer work is, we wrap the soft actuator, the elastomer and the strain layer with a Kevlar thread, mostly because it is very strong, and with Kevlar thread, and to get the configuration, if we change the configuration of the Kevlar thread, means like if we change the angle at which the Kevlar thread is wound around the actuator, we can see the change in the motion of the actuator. As when from the previous studies, we have seen that from 0 to 30 degrees of cross Kevlar thread wrapping, we can see bending. And further than that, we can see torque and extension also. Then after that wrapping of the Kevlar thread, we have used silicon to be cured around these three layers, so that silicon helps to maintain the peer proportion of the actuator and doesn't allow the Kevlar thread to move from its place, and all of these three move relative to each other. And then the end cap of the actuator is then closed with a the same elastomer, which is cured afterwards, and one end cap is used to pump in the pneumatic pressure, the air inside the actuator. So how this in our FEA simulation, what we used is the Abacus software we have used for FEA. So in Abacus software, the Python script can be used to model, which we have used to model our actuator. And the Python script code is really helpful for making it a parametric study to change the fiber angles again and again. And using the same script and just changing the angles can give a new model every time with different fiber angles and different results at the end. So the materials used here are Dragon Skin 10, EcoFlex 030, Silgard 184, and the material properties for non-linear material properties in Abacus, we have used C10 and D1, which can be derived from the Young's model and Poisson's ratio of the material. And these material properties we have found from the previous literature. And these, why only we have chosen these three materials is because the muscles which we are trying to mimic in a body is chosen have lower Young's modulus than a skin and rubber, as you can see in the middle of the scale. So below that we have a silicon elastomer. So elastomers have really low Young's modulus that helps them to give hyperelasticity, due to which when pressurized they can show pressurized and constrained, they can show a various type of different motions. So we have used these three materials which lie in near to the silicon elastomer in the Young's modulus parameter. For finite element analysis, we have used a pressure of 0.06 MPa from which we got from previous literature, and then one side of the actuator is fixed, as we can see in the actuator, where we apply the pneumatic load from the right side that would be fixed in the FE analysis, and a 0.06 MPa would be applied on the inner surface of the actuator, which would be, in real case, it would be hollow. Whereas for mesh, we have used a hybrid TET mesh for the with element type of C3D10H, and for the Kevlar fiber, which is a 1D element, we have used a standard beam element with B31. With analysis settings, we have used as 1000 increments, and initially as 0.01 to 10⁻⁻5 as increment range. This is very important because elastomers doesn't have the same movement as other materials which are higher Young's modulus. They move in very non-linear way, so we need to get the increments correct so that we can capture all the range of all the motion that they are preventing, giving, and also show them in the results. So in the actuator, as we can see in the left hand side, we can see how the bending, how force would be generated by the bending. So to calculate the force generated by bending of the actuator, we have used, what we did was we made a nylon thread as 1D element, beam element, and one side of the thread was constrained, and other side of the thread was tied to the actuator. So this tying, when the pressure was applied on the inside layer of the actuator started to bend and started to pull the fiber. So from that reaction force, we can calculate the force applied, and this would be directly proportional to the force that would be applied on the fingertip of the patient, which would be below the actuator in the real case. So we can see here that dragon skin and Ecoflex from 15 to 19 degree have a similar range of force, whereas Silgard has really low force output. And then we have seen for extension, as extension is also a good part of the actuator which we need, as when we roll our fingers, the upper length of the actuator should increase to compensate the increase in length. So we can find that Silgard increases the length of the Silgard has a higher extension, whereas Dragon Skin and Ecoflex has lower extension. So when we see as from the previous physical literature, the bio literature, biomechanical literature that we refer, we would see that the patient only needs near to 10 to 15 degrees, 15 newtons of force, 15 newtons of force for the actuation, because that is the only difference between the healthy hand and the hand that is affected by the stroke. So here are the material comparison with the other properties of the materials as cure temperature, heat, cure temperature, cure time, color, mixing ratio, and price in rupees. So we can see that temperature is the cure temperature is higher for Silgard, whereas Ecoflex and Dragon Skin have lower temperature. And for heat cure temperature, we have a higher temperature for Silgard, whereas similarly lower temperature for Ecoflex and Dragon Skin, whereas heat cure time is higher for Ecoflex and Dragon Skin. And the mixing ratio for Silgard is 10:1, 1:1 for Ecoflex and Dragon Skin. Price is similar, like near to similar only, with very less deviation. So in conclusion, we have seen that material Ecoflex is better in material properties, as that gives us higher force output, which is needed for the material for the actuation, and lower displacement that will be sufficient for the actuator compensation. The range of 9 to 19 degree of fiber angle was found to be useful in our study in comparison to the previous literature that suggests that the actuator can bend from 0 to 30 degrees, but only from 9 to 19 is proven in our study that it is useful for the patient. The graphs, the values of the force is provided in the paper, so we can go and the person can go and see there, and also find the best output for a patient, that what fiber angle would compensate the remaining force of the patient. Whereas these parameters can be used for affordable and customizable actuator. That is the main point of the paper, that every patient should get a customizable actuator, because these parameters can be used by manufacturers to customize the actuator for different patients, which would help every patient to get a better rehabilitation. And these soft actuators also have a real benefit in that they can be used in daily activities. They can help the patient to do better daily activities that would help increase his life, better his life, due to which he can get a really fast rehabilitation as rigorous rehabilitation is needed. The future scope of the study is finite element analysis of actuator with multiple fiber angles in single actuator, fiber analysis for coupled motion of actuator, and manufacturing and testing with materials to validate the study, and cost-effective fabrication method, and development of effective electronic system to make a fully functional actuator that would help to rehabilitate.
Okay.
These are the references, important references that we use. Thank you.
Okay, Hemkar, you're in time.
Yes,
Participants, if you have any questions, you can type on in Q&A box. So before that, I have some questions.
Yes, sir.
See, Hemkar, you have you optimized the design?
Yes, sir. Sir, we have read many literatures, due to which we found that semicircular design is the best for actuation of the patient, as it has bed in the flat at the end, and also gives the best result in the force output, sir.
So you have done circular cross section, right?
Yes,
so
cross-section.
Can you change? How will be the changes if it is an elliptical one? You know, elliptical shape is also important, because, for example, in the bottom tube pressure gauge, the cross section is elliptical because of some reasons. So have you thought of in that mode?
Sir, mostly
cross section can you optimized?
Yes, the cross section can be optimized easily, because, sir, we are using a Python script, so we can model actuator once, and then we can optimize that accordingly, sir, in the future studies.
Okay, that also should be done. Okay, yes. And also the dimensions, circular. What about the dimensions? Diameter of that tube?
Sir, the radius of the outer radius of the tube is half centimeter, sir.
And also you have mentioned fibers angle, fiber angle, and forces, right? You have plotted.
Yes, sir.
So have you done that? During the analysis, have you done the variation? Have you varied the dimensions? That is the diameters.
Yes, sir, we tried, sir. But sir, as per the human hand, the more the diameter, it would be really hard for the patient also. And with smaller diameter, we can get a better force output for a particular smaller range of that pressure, sir, inner pressure.
So have you checked that? What is the diameter of this?
Sir, half centimeter, sir, outer diameter as half centimeter.
Okay. Then you have applied a 0.06 megapascal, right?
Yes, sir. Yes, sir.
You have taken from the literature.
Yes, sir.
What is your opinion about that? How did you achieve that? In what way?
What, sir? Can you repeat the question?
Now, see, you have taken 0.06 megapascal as the pressure, right? In the analysis.
Yes, sir. Yes,
so that you have taken from the literature. That's what you have mentioned in this.
Yes, sir.
Suppose, now what is the base for that? What is the base for selecting
that? Base for selecting that, sir, I'm not sure, sir, but for the in the literature they showed that for a particular range of diameter that would be
because whenever you are designing something, for example, you should have a payload, right?
Yes, sir.
So whether you are considering payload, because the pressure and all depends upon the payload. That is the main design parameter. What is the maximum payload you can withstand, right?
Yes, sir.
So that should be the input. Then based on that, you can calculate pressure and all, right?
Yes, sir. So that we found that was sufficient because as only 10 to 15 Newton is the difference, and that would be needed for the actuation. More than that would be sufficient, needed for the patient. And at lower angles, only from 9 to 19, we can get that output, sir. Force output.
Okay. Anyway, no questions from the participants, I think. Okay, so we'll stop the presentation. Okay, good presentation, Hemga. Thank you. We'll move to the next presenter.
We have Ratnadeep Pramanik.
Okay, Ratnadeep Pramanik, bidirectional locomotion of a magnetically actuated jellyfish-inspired soft robot.
Is my screen visible and am I audible, sir?
Yeah, it's visible.
Okay, so first of all, good morning to everybody, and it is indeed a privilege and an opportunity to present our work on soft robotics in AIR 2021. So basically, I would like to talk a bit about soft robotics, some of their biomedical applications, and then how do we control the soft robotics in an untethered, non-invasive manner, and what are the computational challenges and the multiphysics during their design, and finally the aspect of bidirectional locomotion forward and backward for a magnetically actuated soft robot that is inspired from an aquatic jellyfish. So essentially it was all hard robotics till probably a couple of decades back, and then the soft robotics have started. That is because of their higher degrees of freedom and their lower weight in compared to the hard robots, and also they consume less power and are ergonomic, which facilitates their use in biomedical applications. They are conceived as the soft multifunctional materials of the future, and the reason they are so popular and are of interest to the scientific community and as well as to the soft matter community is because they have different aspects or different classifications and different possibilities to explore. For instance, in the soft robot, we have essentially a polymer which is very compliant, and it can deform excessively to give us higher degrees of freedom. And in that polymeric base, we can input different types of external filler materials. It could be electrical filler material, it could be electronic, it could be nuclearly controlled, it could be thermal, and it could be magnetic as well. So there are different ranges of options that we have, and it could be two types. It could have the third control, which means that there would be a connection between the user and the soft robot through some wire or something like that. And in case of the magnetic only, we have this untethered robot, because through the magnetic field application, we can control the soft robot. Our work is particularly on the magnetic one, because we aim for an untethered, non-invasive control for biomedical application. So the soft robots, they have different types of biomedical application, for instance in surgical application and microfluidic devices as well. Also they are sometimes used for drug delivery inside the human body. So since they have a lot of use, so for these clinicians and biomedical people, so but the difficult part is their modeling, and particularly how they travel inside the human body or through, say, vascular tubes or blood vessels. So that is one part that needs different types of analysis, particularly from mechanics point of view, fluid mechanics, solid mechanics, as well as the multiphysics, due to the involvement of magnetics as well. So there are works that have been done in this regard already. So the left image, this one, is of a caterpillar caterpillar inspired soft robot, this one, and then this is a jellyfish inspired soft robot. All of them are different, have different types of actuation. For instance, this caterpillar is light driven, so it's optically driven. This one is electronically or electrically driven. This one is again a jellyfish inspired soft robot. This is pneumatically driven, and this is our main inspiration, which is magnetically driven jellyfish soft robot. So this is actually the jellyfish, which is an aquatic swimmer, and it is regarded as the fastest aquatic swimmer, and that is why we choose this as our motivation. And this work has already been done. So they have like developed, formulated a design, and this is the photograph of the fully developed soft robot. And they have what they have shown is that under different magnetic fields, so these are the direction of the magnetic fields, this 10 millitesla and minus 20, so these are the values that we have. So what we are able to get is due to the application of external magnetic fields, these members, these are called lappets, boat lappets. Why we call jellyfish boat? Because it is inspired from a jellyfish and it's a robot, so we club the two term and we say it's a jellyfish boat. And due to the magnetic field, they deform, and this is it can be pre-programmed and it can be predefined shape morphing under magnetic fields. So essentially it is non-invasive, and it is also untethered. Now this group has already put up dynamic models. However, these are not very sufficient because we do not know the physics of the fluid field around. Also, we do not know the stress field, or we do not know what is the exact magnetic forces or torques in the body. So for that, we require a fluid structure interaction magnetodynamic model. And also we have this computational, we do a computational design, and to achieve this bidirectional swimming, as well as in general to study the kinematics of such a soft robot based on jellyfish under magnetic actuation. So this is we do a two-dimensional study. So this is the jellyfish boat that we have, and this is the direction of locomotion. These are lappets, these members are lappets, and they undergo flexural deformation under this magnetic field. And this is the viscous liquid all around. And then for the solid mechanics, we have the Navier's equation, and we solve it using finite elements. For the fluid, we consider an incompressible form of complete Navier-Stokes. Also, we do it using finite elements. And for magnetics, we use the Maxwell's equation, and we have an in-house boundary element code for that one. And we do a computational multiphysics numerical simulation. We use a point collocation technique using Lagrange multipliers to tackle the boundary effects, the solid fluid interface. And because the deformation is very large, we have a fixed grid method and not a body conforming mesh, so that the mesh deformation is not there. And finally, we have this in-house Fortran codes for solving the multiphysics of this simulation. So to understand this one, first of all, like this is symmetric. The entire thing is symmetric, like the solid mechanics as well as the fluid mechanics is symmetric. That is one assumption that we state initially. Initial deformation speed is 0. The left, right, and bottom walls are no slip conditions, and the no slip boundaries, and the top surface is a 0 pressure gradient. There are 3 phases in the jellyfish boat motion. One is a relaxation when the lappets relax. There is the contraction when the lappets contract. It's the opposite. And there is finally the glide when there is no structural deformation, but the robot just glides through the fluid, similar to a Stokes drag. So these are the examples of 2 locomotions that we have. So this is one locomotion that we this is the forward locomotion, and this is the backward locomotion. The right hand side video is a backward locomotion. Now we are able to get these 2 different types of locomotion in the fluid for the jellyfish boat just by changing the external magnetic field. The fluid parameters, the solid parameters are the same. So this is the backward swimming that we have. The red is the first cycle, the blue is the second cycle, the green is the third cycle. These are the different types of magnetic fields variation over time that we apply so as to observe a backward swimming. And the legends, what we have in the legends is the speed, the average speed. and we see for different types of waveforms the speeds are different. So we get a reasonable speed of 4.3 millimeters per second in the backward direction. This could further be increased by a suitable choice of and a more optimized choice of the magnetic field. Similarly, forward locomotion can also be achieved in these soft robots. We have something like 7.7. We are able to achieve 7.7 millimeters per second for the forward case, and again through different choices of magnetic fields. So the forward and the backward swimming, as well as in general kinematics of these soft robots, has been studied by us. And I'll just conclude with this one. So essentially what I discussed was a state of the art soft robotics, and how do we do them using computational design, and how we are inspired or motivated from aquatic animals such as the jellyfish, and we computationally design a magnetically actuated swimmer robot for biomedical applications, futuristic biomedical applications, and we are able to achieve a bidirectional swimming kinematics. And this is due to actually the temporal asymmetry. There are two types of asymmetries that could be possible in these cases. One is a trajectory asymmetry, and one is a temporal asymmetry. Now the temporal asymmetry, this is more dominant in high Reynolds number, because in that situation the inertial effects are significant, and the aspect of bidirectionality comes into picture only in considerably high Reynolds number. At least we should have something like more than one. In the Stokes flow regime, this is not possible, and that and those cases only the trajectory asymmetry plays the dominant role. Here we utilize only the temporal asymmetry. You can see from this image that the area swept under these small these areas are very limited, and the only driving force is the temporal asymmetry. So temporal asymmetry is the root cause for this bidirectional swimming kinematics. So our future aim is to observe this bidirectional swimming for another type of soft robot, which is octopus inspired soft robot. So there are lots of experimental works that have been done in this one by different research groups around the world, but the computational modeling could be something that could be reported also. And from our perspective, we are looking forward to extend our present framework of computational simulation to a 3 dimension, and that is what we are working towards right now. So yeah, so thank you for your kind attention.
Hello. Hello, you were before time anyway. You see, I'll ask one question.
Yes, sir.
Okay, what is the size of the jellyfish you have taken for your simulation?
So it's 3 millimeters.
Then what is the? How can you specify jellyfish? That is the lappet size, or?
So should I share my screen and do that, or
No,
just...
you just
okay. So the jellyfish boat is actually 3 millimeters. So each lappet is 1.5 millimeters. So and since it's 2-dimensional, we have considered, and it's symmetric about the mid plane. So it's 1.5 plus 1.5 equal to 3 millimeters.
Okay, so you considered all the inertia effects. What are all inertia effects?
Yes, sir. All the solid as well as the fluid inertial effects have been considered.
Okay, so how did you update the Lagrangian boundary conditions, the equations of in the magnetic field?
The magnetic field is... Sir, actually we are using for the solid, since it's a large deformation problem that we are doing, we are using an updated Lagrangian scheme for that one, because there is this geometrical nonlinearity involved. And for the magnetic field, we...
Okay,
Yes,
how can you do that? Boundary condition, how can you change for the updating?
We do not change the boundary condition. We just update the position of the solid structure. So we say that the deformed configuration is the current configuration.
Okay. So then, what about the maximum force generated torque? I mean, joint torque, or maybe you have done the 2D simulation, but what is the maximum force generated?
So the force values I cannot tell you right now, like I do not remember it.
Because you have mentioned the speed, optimal speed you achieve, right?
Yes.
So like that, how much force, because that is required for lifting.
Yeah, Yeah, actually force is actually zero. The reason is it's a uniform magnetic field, so in plane forces are not there, but obviously there is a magnetic torque, and there are some
Definitely,
values
definitely
for,
will be there.
yeah, definitely the torques are there, but sorry sir, I do not remember the values of the torques.
Okay, okay. Okay, any questions from, okay, I think 2 questions. What is the magnetic actuation so important to actuate jellyfish robot? That's the first question from audience.
Okay, so I will take that first. So the reason we choose a magnetic actuation and not other types of actuation, for instance, is electrical or pneumatic or thermal. The reason is the magnetic actuation is non-invasive. So there needs to be no connection between the external operator or the user and the soft robot. In other cases, there needs to be some sort of a wiring or a connection between that one. So for biomedical applications, when these soft robots are used inside the human bodies, so we would like to have a non-invasive control, and that is the reason we use magnetic actuation. So that's the answer to the first question. Can other magnetic actuation methods be used? Yeah, it can be used, but it would be invasive. And for other types of applications, definitely that can be. For example, for microfluidic applications, it could be possible. I'm not very sure, but for biomedical applications, magnetic actuation is one of the appropriate or maybe I would say generally accepted way of actuation.
Okay, second
The
question,
final
can
question:
other,
is this study limited to computational modeling or experimental validation is also planned? Well, the work that I showed right now it has already been experimentally demonstrated, and it's a research group in Germany. But we are doing only the numerical modeling for the moment. But later we are looking forward to incorporate both.
okay, so you are planning for experimentation also after the 3D simulation, right?
Yes, through some collaboration probably.
Okay, no more questions. Then we'll move to the next session. Thank you. Thank you
Thank you
for
so much.
nice presentation.
Thank you so much, sir.
We move to the third person. Okay, that is Vineet. The third presenter is Vineet. Helical SMA actuator based artificial muscles and arm with sliding mode control.
Yes, sir. Hello, sir.
Yeah. Hello. Yeah. It's visible.
Good morning. I am Vineet. I'm going to present the paper titled Helical SMA Actuator Based Artificial Muscle and Arm with Sliding Mode Control. And the authors being myself, Saurav Karmakar from IIIT Hyderabad, and co-authors being Dr. Kim Jesop, Dr. Anand Kumar Mishra, and Dr. Abhishek Sarkar. Coming to the literature survey, in Zhang et al., they have used two muscle fibers and a bias spring to lift 500 grams of weight, where in our case we have used only one SMA fiber and we could be able to lift about 64 grams of weight. And in Zhang et al., they are able to produce a contractile force of about 230 newtons, where we have obtained about 0.62 newtons, which is 64 grams at the end of the end effector. In the paper of Park et al., they have used a diamond structure equipped with two SMA wires, which could generate about 56.3 Newton force, and it took about 3 to 5 seconds to lift the object, whereas we could generate about 0.62 newtons in the same time. We were using a maximum current of 4 amps. Coming to the objective, our objective was to mimic the human arm such that we could produce an alternative structure for a small scale artificial arm implementation with a control. And two was to consider the force generated by the SMA spring in the dynamics of the system. Three was a control methodology to control the artificial muscle Here we have chosen an sliding mode control as it makes an higher order control problem into a simpler one. The chattering phenomena occurring in SMC, which causes a disturbance in our system, is decreased by utilizing linear saturation boundary condition layer function. Before we dig deeper into the I would like to discuss something about shape memory effect. The shape memory effect is the ability to remember a predetermined shape even after several deformations. The shape changes with temperature variations are mainly attributed to phase transformations. Firstly, the SMA is thermally processed to receive its permanent shape. Then afterwards, it is deformed and the intended temporary shape is fixed. This process is called programming. The permanent shape is now stored in a while the sample shows the temporary shape. If you heat up the SMA above the transition temperature, this induces the shape memory effect. Here in our artificial muscle, we have used the nitinol as artificial muscle. This shape memory alloy is made up of nickel and titanium. It is widely used for the manufacture of surgical devices and implants because of its biocompatibility. The nitinol wire is wound onto the grooves of the bolt and held tightly in place with the help of its nuts. And the bolt, along with the nitinol wire wound onto it, is heated in a furnace to a temperature of 150 degrees Celsius or more for a few minutes and rapidly cooled in a water bath. This process helps the nitinol wire to acquire the helical spring shape due to the thermomechanical properties that we discussed before. This is here is a schematic diagram of our experiment. Here we use a potentiometer as a feed mounted at the joint, elbow joint, which we use it as a feedback sensor, and where we calculate the error out of it, and then we calculate the sliding surface. Along with it, we find the control law too. Then that control law is utilized to give control the current via a Darlington pair amplifier. The Pillai et al. Has an deduced equation to measure the force generated by the SMA spring. The spring outer diameter, number of turns, the shear modulus, phase transformation factor, and Martin-Side factor. The Martin-Side factor has different values when the SMA is being heated and is cooled. This equation is later utilized to derive the control law of the sliding mode control and the dynamics of the equation. Here, the dynamics of the system is quite simple and similar to that of the dynamics of a simple pendulum. The force generated by the SMA spring is utilized to make the final equation given by equation number 3. The sliding mode control can be viewed as a way to reduce a higher order control problem to a simpler one, for which there are known feedback control methods. The sliding mode surface is deduced using the estimated error in the position given by equation number 4. where lambda1 and lambda2 both are user-defined variables. The final control law utilizes the dynamics of the system, the force generated dynamics of the system, the force generated by the SMA spring, the sliding surface to achieve the objective. This control law controls the current provided to the SMA spring via the Darlington pair amplifier. Here is a result showing the position versus time graph for experiment, and the plus or minus 5% convergence reaches at 5 seconds, and it settles after 25 seconds. Here is a graph of the sliding surface. It begins from right to left. As you can see, the sliding surface comes to 0 and chatters here, which is reduced to a small fraction. Here's a video of the experiment. Here the arm is carrying a load of 64 grams. Well, I can conclude that our artificial muscle is lightweight, which weighs in around 70 grams and can lift up to its own weight with a single SMA wire. We can add a few more SMA wires in parallel to the existing SMA wire to increase the load, which makes it a little dynamic. The maximum contractile length is 115 mm, and this system could be an alternative structure for small-scale artificial muscle implementation with control. Thank you, and thank you.
Yeah. So, the first question from the audience, that is, how was the load that was carried out, 64 grams?
How was the load?
No. So your payload is 64 grams, right?
Yes, sir.
The question is, how was the load? How do you achieve that load? So that means, what is the specification of the spring? That is, I think that is the meaning. No, for achieving 64 grams, then which type of spring? And what is the specification of spring?
We have used an ethanol SMA wire, so specific. I still did not understand the question. Carried 64 grams. We have experimented with different payloads. We have started with basics with no load, and we have arrived to 64 grams. And later we have pushed to 100 grams to where it could not lift to the desired position.
Okay. I think
64 arrived. It was due to trial and errors.
Okay. That's what you answered. Then second question, SMC, are you using acceleration feedback in the input design?
Yes. Actually, as you can see, we have used and later we have used the change in the contractile length as a feedback tool, along with the position of the arm with the potentiometer.
You have done the position control, right?
Yes, sir.
Okay, you have done the position control.
Yes, sir.
Okay. So I think I have one. I'll ask one question.
Sure.
What about the hysteresis effect? That is one of the important issue, right? Have you?
Yes, sir. Yes, sir.
What is the hysteresis effect on that your system? Have you analyzed that?
About the hysteresis effect, where we are using this sliding mode control, which would like overshadow the hysteresis effect. Like
It's not clear. How did you account that hysteresis loss in your control?
We will not accommodate the hysteresis into the control.
Okay. So I think no more questions. We will stop the presentation. Okay. A good presentation. Thank you.
Thank you.
So the next presentation by Atul Thakur.
Presenting
ready.
author is Satyendra Nishad. Can you please make this correction?
Hello, Professor Raji.
Yeah.
Can you repeat?
Presenting author is Satyendra Nishad. Please make this correction in your notes. First author.
Yeah, so my voice is audible and my screen is visible.
Yes.
Okay. So good afternoon, everyone. So I'm from IIT Patna. I'm here to present my paper titled Lizard-Inspired Quadruped Robot based on mechanism for wall climbing. So the authors for this paper is myself, Dr. Raju Haldar from IIT Patna, Dr. Jagannath Banda from IIT Indore, Dr. Rajarshi Ray from IIT Kolkata, Dr. Anshuman Bhattacharya from IIT, and from in a hostel scenario,
Your screen is Satyendra,
for example, drones.
Yeah. Satyendra, please hold on. Your screen, you come out of slideshow. Okay. Yeah. Now you go to view command because we couldn't see your slides moving. Go to view at the top, view tab.
Okay.
View.
Yeah,
yes,
view.
And reading view.
Reading
Fifth
view.
item on the left. Reading view. Yes.
Okay.
Yeah.
So
now
is it
please
now
go to the next slide. We'll see whether it moves. Okay. Thank you.
Okay. So the motivation for our work we got from a situation from a hostel situation. So in a hostel situation, the current available technologies such as drones, they fail miserably because they make a lot of noise. So in the place of drones, if we have some robot that is very similar to house lizard, then the robot can be stealthily enter into the crisis scene, and it can send the necessary important information to the security forces. And after getting the this important information, the tackling this task will be very much easy for the security forces. So this is our inspiration, and in this paper we have tried to design and develop a lizard-inspired robot. So from the literature review, we have come to a conclusion that there are two main components. That is and the second one is, so talking about the modalities, techniques, microscience, adhesives, and microfibrillator adhesive. So each of these techniques advantage the locomotion mechanism. So
voice is breaking.
We have tracked robots and we have wheeled robots, and all these robots have the advantages. So for our work, we have chosen and locomotive. is to build a robot, which is a part and the real result. It has a sticking and peeling mechanism. It can climb vertically, and it has onboard power supply and electronics. And so, talking about our design. So, our design, as I mentioned previously, inspired. When we see a real lizard, it has its body is flexible and it has a lot of degrees of freedom. So, making exactly similar difficult. So to simplify the problem, we simplified the lizard design, as you can see from these figures, and we have come to a design where this robot has only 6 degrees of freedom, and we have also removed tail from the design, so as to simplify the design even more. From this picture, which is schematic, we can see the robot has the front leg, the back leg, and the spine. And this schematic is detailed in the CAD model. So in the CAD model, we see the front leg, back leg, and the spine. On the front and back leg, we have a foot on each side, and all the electrons on the spine of the robot. And here in this figure, we see the detailed design of the foot of the robot. So we have utilized technologies such as 3D printing, laser cutting, and PCB printing for fabricating our robot. So these are the pictures of the machines that we have used. And the materials that we have used are ABS, POM thermoplastic, and acrylic plexiglass. So on the left-hand side figure, we see the components of the foot that is fabricated using the ABS material and 3D printing, and they are then properly assembled on the robot to have the feet of the robot, which is detailed over here. In the right-hand side figure, we see the fabricated leg and the spine. For locomotion, we have utilized trod gate. So in the left figure, we see the schematic for the trod gate. So in a trod gate, we basically lift 2 diagonal feet, and then and the rest of the feet are aloft the surface, and the raised foot are then put forward and they are attached, and then the cycle continues. So this is how the trod gate works. And on the right side, we have the gate diagram. In this gate diagram, we can see the horizontal black lines. So these black lines shows the foot that are in contact with the surface. So for controlling the robot in trod gate, there are 2 key motions that we have to give to the robot. The first one is the synchronized motion between the front and the back leg motor. And to synchronize this, we use the phase lag coupled oscillator, and whose so theta f represents the angular displacement of the front joint, and the represents angular displacement of the rear joint. And we have a factor gamma over here, which is so the neutral position of the front and back. So as here the horizontal lines we can see that's position, and we can add gamma so that it get offset, and by offset we make the robot steer either in the left or the right direction. On the right side, we see the line of sight based guide that we calculate the error E psi, and then E psi to calculate this gamma offset. Go to the goal position. So also on the robot, electronic components. Out of them, we have 6 micro an Arduino Nano microcontroller, and a shield for interfacing the electronics. We also have HC05 Bluetooth module wireless communication, and we have power supply and the associated electronics on the robot. Results: the robot a slope of 90, acrylic plexiglass sheet, and the climbing distance 35 centimeter. We support climbing payload, right? What climb attached to it through the thread. So now the video. Okay, so we'll move to the next. And in conclusion, we have designed a mechanism, and we see that it is properly working. And in our robot is able to climb 90-degree slope even without tail. So while making a wall climbing robot, tail is part of the robot that enables the robot to climb vertical surfaces with a lot of stability. But in our case, even after omitting the tail, we could climb 90-degree surface. And steering is also possible in our robot. And if we compare our robot with the other work that has done, various authors, they have utilized a tail or an additional degrees of freedom in the center to get the steering. We are able to steer even without incorporating any additional actuator. And we are working in the direction to make our robot climb, basically transition from one surface to the other surface. So from one wall to the other wall, or from a floor to a wall, or from wall to a wall. So the work is also going on in that direction. We also plan to replace our current adhesion material, that is pressure sensitive adhesive, by a microfibrillaർ adhesive, because this microfibrillaർ adhesive is to the actual lizard's design, and it can work on a wide variety of surfaces. So advantages with this technology. So we are also planning to replace other material with the microfibrillaർ adhesives. And as a tail is very important, we are also planning to add tail to our robot, and it will definitely improve the total stability, overall stability of the. We are planning, since we are targeting a hostage scenario, we are planning to develop a swarm of such robots. We can get a lot of information from a crisis scene. So that will again be helpful. Okay, so that's it from my side. Thank you everyone for listening me patiently. If anyone has any question, please feel free to ask. Thank you.
Okay, good presentation. So I have some questions. So then
yes,
first move to the participants. So how did you arrive that offset gamma? You know, you have put up some correlation in 7th slide, right? How did you achieve that gamma offset?
Yeah. So, here we see and what the
we are not able to hear you. It's
so
can you stop your screen and then you can speak, please?
Yeah, your voice is breaking.
Okay.
Yeah.
Okay. Now I'm audible?
Yeah, audible.
Yes, sir. Yes, sir. So by choosing a gamma value, we actually, yeah. So all I'm saying is that by choosing a gamma value, we actually offset the direction in which the front and back legs are oscillating. So if we give gamma value suppose 0, then the front and back leg will be on the neutral position. So it will not have any offset. So it will just go in the forward direction. But if we give positive or negative, depending upon that, the robot will either turn to the left or to the right.
Because you have taken gamma is equal to some k into E5, right?
Yeah.
So what is that k? K, how did you select? Based on what criteria?
So k is like so we tried we
Okay, fine. See, then what about the total, weight of your robot, total weight, not payload, what is the total weight of your system?
Yeah, so the total weight of our robot
50 grams. So 50 grams, how did you design it?
Yeah. So it is 150 gram. 150.
150. Yeah. 150 gram. How did you design the mechanism that for the 150 gram? How do you design the sensitive? That mechanism, adhesive mechanism. Because you have 4 contact point, right?
Right.
So for contact point, how do you suppose the weight is 250? You have taken trial and error, or is there any specific methodology to find out that?
Weight of the robot. Okay, so at present we have we are going with the trial and error methodology. But yeah, I think we are also we have also done the stability analysis of the robot. So by keeping the values, the height, weight, and the dimensions of the robot, we can decide that value. So if it is stable, if it falls under the stable region, then we can keep that weight.
Okay, so one curious question from Professor Raju. So it's a good experiment work. So how are the others from so many organizations involved in this work?
Yeah, sir. So this is actually a DST funded project, imprint project. So since this is a work where we need a lot of expertise in the design side, in the electronic side, in the communication side. So we found expert people in our group, and I think that's how we are going on.
Okay.
So basically, to have expertise, I think this is done.
Okay. Thank you. Then next question. While climbing vertically, is the robotic lizard bidirectional? Yes.
Bidirectional.
Yeah.
Mean to say it can go forward and backward.
Yeah.
Yes, sir. It can go forward and backward.
Okay. The next question: how the tail helps helps in stability? What does stability mean in this case?
Okay. So, sir, while climbing surface, so the video that I showed, it is on the 90-degree surface, but we have tried our robot on lower slopes also. So if the slope is lower, the robot will climb comfortably. But as the slope increases, actually the CG of the robot it shifts like the front. It actually tends to rotate about it creates a moment. So that makes the front leg to come out of the surface. And if that comes out of the surface, then the stability is lost, like adhesion is lost, and we have a weight of the robot, so it comes down.
Okay.
So,
okay. It's a shortage of time. One more last question. That is, the hostage scenario don't have plexiglass to climb. How to plan to address the challenge of various types of wall surfaces?
Yes, sir. Yeah, that's a very good question. So, sir, since we are also very new in designing these robots, so So to answer your question, actually, there exists a adhesive material that I mentioned in my presentation, microfibrillaർ dry adhesive. So that works on all type of surfaces, and that is actually very close to a real lizard's food design. So if that is incorporated, then it will surely be able to climb different kinds of surfaces. But yeah, with the current technology, pressure sensitive adhesive material, we need clean surfaces. As I mentioned in the beginning, with whatever technology you go, it has some pros and cons. So the pros, it has pressure sensitive adhesive that it is readily available and it is very cheap. So we can start our work, and as our robot gets matures, then we can replace its sticking mechanism with a microfibrillaർ adhesive.
So with one more last question. See, will the clamping mechanism work for the kind of textures on walls when Avni Damchi? Will the clamping mechanism work for all kind of textures on walls?
All kind of textures. Okay, can you elaborate all kinds of textures? What does it mean?
Texture? No, there may be some surface textures. Now, whatever be the surface texture, will it work?
Okay, so surface textures, what I understand is that it will have different roughness. It will have irregularities. Yeah, so of course, this current pressure sensitive adhesive, this will not work. But if you replace it with the, as I said, microfibrillaർ adhesive, it will definitely work. And also, where like since we have legged locomotion, even this can work, because in legged locomotion we have control on our each of the legs, unlike the wheel or the track. If there is any obstacle, then we can climb over it and we can surpass it. So
okay,
right, so that can be done.
Okay, fine, good presentation. Then we will, because of shortage of time, we'll move to the last presentation.
Thank you, everyone.
Presentation by Dibyendu Kumar Das, convexity and contrast graded gate mechanism for silent object detection. This is the last presentation. You can start.
Please unmute.
Am I audible?
Yeah, audible.
Yeah, am I audible?
Yes, please. Are you on full screen, or you are? I think you have only enabled application. Can you please? Okay, go to the next slide.
Is it a full screen now?
Yeah, it is full screen. Can you go to the next slide? We'll just check quickly. Yeah, please start. It's working. It's working.
Okay. So good noon, all of my chairs and attendants of AR 2021. I am very pleased to showcase my presentation in AR 2021. So I will present our work named Convexity and Contrast Guided Gate Mechanism for Salient Object Detection. Our co-authors are Sahadev Seeth, Dr. D.N. Roy, and Dr. Somajyoti Mojumdar from CSIR CMARI. And we are also from Academy of Scientific and Innovative Research Institute. Okay, so our objective of our work is actually detect the visual salient object of an image based on the human visual attention system. So when I am talking about human visual attention system, it is obvious that there have some neuropsychological behavior of human visual system. We have to modeling it. So for survey of that neuropsychological behavior of visual attention system, we go for the Gestalt psychology. Gestalt psychology, according to Gestalt psychology, convexity of an object is the most important cue to attract human attention. So according to that psychology, we make a model which can extract the salient object from an image. So this is our main motivation and objective. Later I will elaborate how this will work. Yeah, so for visual attention modeling, we have to concentrate on two types of visual attention. The first is bottom up, another is top down. Bottom up attention is the intrinsic parameter of the image which responsible for attract the gaze of human eye, and top down is the human behavior like memory, his perceptual behavior. This type of thing is called top down approach, but our approach is a bottom up. Actually we modeling our approach using the bottom up visual attention modeling. So from the decades there have a different type of mathematical modeling of visual attention system has been incorporated to find the salient object. The first is biologically plausible, then space or spatial based salient object detection technique, then object based, and the new technique are the neural network based technique, which is still going on to robustly extract the salient object based on the human visual attention system. So here are some example which is uh, taken from their literature survey. These are the biologically plausible result. These are the space-based result, and these are the object-based result. So why we should go for the convexity? Okay, and why should we go for our gate-operated convexity for salient object detection? So we can see there have a lots of image which has multicolor, multiple object, and non-uniform appearances, or complicated shapes. So in that case, conventional contrast-based model or the object-based model are drastically failed. Okay, so we are target to integrate contrast-based model with our convexity model and make a final saliency model and achieve a far better result for them. So this is our problem statement, and this is our methodology. So first, we segregate our input image into two parts. First is to find the saliency score on the contrast level, and second is to find the convexity of an object. And after that, using a gate operation and gate operation, we are fusing them both and get the final saliency of an object. So now go to the contrast-based saliency. So to compute the contrast-based saliency, we have divided our image into the three color space. The first is the RGB. Conventional contrast-based saliency only consider RGB, but we are consider RGB, lab, and HSB also to get the more robust salient object from the scene. Okay, so after getting and from that we are getting the mean intensity of the pixel value from all of the three color space. So after getting the mean intensity of the pixel value of these three color space, we are going to calculate the saliency score of an image based on the contrast-based saliency by this equation. You can see that equation. It is nothing but to calculate the distance metric based on the contrast, and then sum it and then sum over to find the saliency score. The first row is the input image, second row is the saliency score of RGB color space, third row is the saliency score on HSV color space, and the last row is a saliency score of labs color space. We are sum it over and get the final saliency score on the contrast level, and we get this image. You can see this is the final image we can get. But see, on the lower part, in the lower part of that slide, we can see there have a some background residue still here. So our method is not fully achieved or extract the salient object using only the contrast-based saliency. So we have to remove those residues, background residues, using some method. So for remove those residues, now we go into the convexity. So for finding the convexity of an object, first we have to compute the corner descriptor of an object. So for that case, we use first algorithm. to find the corner point, and after finding the descriptor of that object, we are going to Jarvis-March algorithm to find the convex hull, to build the convex hull algorithm to find the convexity of an object. So this pointer x1, x2, x3, x4, x5, and x6 are the descriptor point, and we are implemented Jarvis-March algorithm, which is also called gift wrapping algorithm, to find the convexity of an object. So Jarvis-March algorithm actually work in such a way that it will find a point, it will join all the point and check no point is on the left hand side. So first x1 is connected to x3, x2, and checking that whether any point is on its left side or not. Yes, there have a 2 or 3 more points are on the left side of the x1. So it will cancel the connection between x and x2 and going to x1 and x3. But still there have a 2 point on the left side of the x1. So it will cancel those points also and going to x5. And there have a no left point further, and it will connect all those points successively and build a convex hull algorithm and wrap an object in a convex hull and remove all those points which are middle of that object or the descriptor. So this so now we have completed the convexity of an object also. So now the total methodology is look like that. This is the original image. This is the ground truth of that object. I mean, this is the image and this is the salient object. Using Jarvis-March algorithm, we find the convexity of an object. Then we find the saliency score of that convex map of that image, and we find this image. But see, there have some discrepancy between the ground truth and the convex hull map. This this black color, you can see that this is the extra added residues. So we have to minimize this residues from that image. Now going to the multi-channel contrast with saliency core, and you can find this this one, which I've also talking about in my previous slide. So you can see that there have some residues in the lower part of that image also. So we have to integrate those images using the AND operation, and we can find those. We can find this final salient object, and which is more similar to the ground truth and achieve state-of-the-art method than other method. This is my result. Actually, I have calculated precision and recall and F scores in two data sets actually, MSRAB and ESSD. ECSSD and MSRAB both are publicly available benchmark dataset for salient object detection, and we was applied our algorithm on those images and find that our method is achieve for more better result than others. These bold colors represent our result. You can see that for recall in ECSSD, SF is achieve better result than us, but for the precision in F score, we are getting much better result for other state of art work. This is the quantitative result, and now the qualitative result is also this there. First row is represent the image, second row is the ground truth, and these all are the state of art applied to detect the salient object, and last is our result. So we can achieve a more better result than others. And yeah, finally we can say that actually we have to integrate saliency and convexity in a single channel to find the salient object from the scene. But we have faces some issue here when the image is more complex and more cluttered background. Then our algorithm also failed. Like you can see that this book is the most prominent and salient object here, but it will not be extracted fully using our algorithm. So our algorithm is failed here. So we have to work on more to find the different feature parameter for extracting the salient object using the neural network or any other psychological or any other psychological effect by finding the decision theoretic approach. So this is actually our work. Thank you. Please feel free to ask any question.
Then I have one or two questions. Then we'll move to the participants. See, have you checked for the very small, you have taken a set of objects. Have you checked for the very small objects?
Very small object
can you say up to very small, for example, insects or maybe that kind of objects have you? Because
no,
the efficiency of this particular algorithm for very small objects.
No, we are not actually searching for a very small object. Actually, we have already applied our algorithm on available data sets. Okay, so that data sets are set their resolution of that image on 240 into 300. Okay, and they are actually the data sets of different type of outdoor and indoor images. So there have been no provision till now for the very small object.
Okay. How many you have used two data sets, right? How many data you have taken for the analysis?
Yeah, sir. Actually, in ECSHD and MSRIB, both the data sets are actually keep total of 5,000 of images. Okay, so we apply our algorithm on the 5,000 images and get our result on a precision and recall basis.
Okay. To the audience, then question. I think this question is for you only. Can you please elaborate the peeling action by showing an image of the robot? What is that?
So this question is for the previous guy, I think.
Previous. So any more questions from audience? So okay, thank you, Bendu Kumar.
Thank you.
Nice presentation.
Thank you, sir.
So this is the last presentation. We have to wind up. I'll move to Professor Ashish, sir.
Yeah, thank you, Professor A.P. Sudhir, for chairing this session. It was very nicely conducted. The marks, please send it to Rajiv and myself.
Okay, sir, I'll do that.
Yeah, so thank you again for conducting the session. Please do come for the afternoon sessions also.
Yeah, sure. Thank you, sir.
Okay, thank you, everybody.
Thank you, Rajiv.
Thank you, sir.
So thanks to everybody who presented in this session. Now we can break for lunch. Now we can meet at 2:30 because after lunch we have 5 papers. No, sorry, we have 4 papers only. Okay, and then we have a plenary talk at 4 o'clock. So we had kept some free time in the afternoon, mainly because if somebody misses out a paper and because of connectivity or whatever reason, but that has not happened strangely. So actually we have some free time in the afternoon. So let's meet again at 2:30. Okay, so we'll meet at 2:30 and we have 4 papers. We'll finish by 3:50 and then we have the last plenary talk at 4 o'clock. After that, we have the closing session at 5 o'clock in which you can give your feedback and we will close this conference this year. Okay, so Rajiv, is there anything else?
Regarding the posters, today we had 3 posters.
Yeah.
So those people, if they want, like the networking area will be open as soon as we close this. And people can go around the posters. They are listed on either side of the networking area. And if you meet the person from that particular poster, you may just ask them any questions if you have.
Okay, then let's close this morning session and have lunch and then come back again at 2:30. Please do come back at 2:30 for the session. And then there is a plenary talk at 4 o'clock. Okay, let's break for lunch.
Okay, thank you, sir.
Yeah, okay.